Thank you. For the opportunity to be here and present this school. I'm excited. So, this is going to be my basic lecture. I'm not going to talk too much and not even the simple slides of my own work. So this is more about historical view of some of these, not historical view, but some of the classic models that have been put forward through the years in proposing neural models, neural network models. So try to make build a theory about how neural networks are able to perform some basic cognitive functions such as working memory and decision making. And I figured this would be like something maybe useful for the students as we are in a situation now in neuroscience where there's new tools arriving experimentally that are bringing these models that were sitting there like in our, as the basis of what we think about neural network function. And they're bringing them back because now these methods are giving us the tools to actually go on and test them. And this is something quite interesting, and there's quite a few publications recently that have done exactly true. So essentially what I'm talking about is really four special advancements that have been made experimentally or even conceptually. One would be optogenetics. So now we're able to perturb instant circuits in a sort of quite global way. So you're able to perform optogenetics and induce changes in behavior. And that's something that is crucial for models like this to be tested. I'm going to show you some examples of what this thing has been done. Another of the advancements that have been presented in the field recently is this large-scale recording. So now we're able to record not just one or a few units, but hundreds of neurons at the same time. In single trials, we're able then to think about how that circuit, so we have a more proper way of thinking about trial-by-trial changes in activity in the circuit. And that's something very powerful that I can strain model. That's a way in which these models can be tested experimentally, because we have these multi-output recordings or calcium imaging recordings that give us lots of neurons in one single trial. Then the other thing I want to highlight is this focus on behavior that we're seeing in the field too. So we're not more concerned about whether animals get it right or wrong, but in what way we do that, and what are the errors they do, or how specifically they perform their responses. And all those things can be captured in this model from this training. And finally, what we've been seeing now together recently in the talks here is this view of training networks. So coming top down, and being able to say, okay, this is the function we want, what would be the network? And these other models that are, as Zhao mentioned, these are more bottom up. We're thinking about how to build models based on our knowledge of physiology. There's a way where they should meet, and we should put them together. And that's also challenging in society. This. I'm going to go through some of these models. I also think that this ION is a particularly good place to present this because most of these techniques I said are very, very highly developed here. So you get the experiments that are maybe going to test further all this model. Maybe you can get ideas from displaying them. So this is a presentation. I want to say that from. It's a presentation I have made in a Python notebook, so you're going to get it. So everything here, you will get all the slides, but all the code that is behind the slides. So you can run the simulations after this. Okay, so I'm going to go through these models. Okay, this is just like the overview of you can come back to this when we're done and you get the references, the links to all these papers. You'll get this on, you don't need to fix this, you're going to get it on your email. Okay, so we're going to see first on Cortical networks, like the basic structure, what could it be, and what do they do, and how can we tell different regimes. We're going to think about AI networks, those are the common things to do. That's one of the first, one of the every computational neuroscientist is interested in how to know about that model. The vision stabilized network is something that has a lot more recently, but it's the also response history, and they're very interesting to compare. We're going to go through that. Then we're going to look at memory. So this first part is not so much cognition; it's more about like the basic dynamics in the cortex. But then we're going to start thinking about memory and decision making within ring attacking networks. And finally, we're going to go to continuous memory in ring attacking networks. And my last plan is to link this to lower environments that you show what's that means. So, okay. So when I'm talking about memory or cognition, this basic mechanisms of cognition that we're going to be talking about something quite specific, which is a very broad thing. You've seen some of this. This is very low level because we're going to try to explain the problem of this method. So we can go very far. We can't yet go to all the things about experiments. For now, we're going to focus on some very simple things, like just remembering. This is one of the experiments in the Ashita lab. Monkeys were trained to memorize one shape, and then after a delay, and that's the crucial part of this task, they were presented now two objects, and they had to pick with their hand, they had to point at the object that was paired with this point. So they, through learning, they have learned that this object is paired with that one. So at this point, the right answer is this one. They learn the associations, and then when they're well trained, they are doing this task while they report in extrastriatal cortex in area IT. That's an very advanced stage in visual processing in the temporal lobe. And yeah, so this is the crucial part of the delay, because in this area, what animals have to do is to keep in mind that shape, maybe not the shape, but that category or some identifying features of these object or of the pair that they are expecting to see. Something needs to be stored through this delay in order for the monkey to be able to task. And monkeys are very good at this. So where is that signal? And that's where they found in this area IT is where they found neurons that did show some knowledge about what the item was. So this so we're seeing this one specific neuron recorded in this area. And we have the two conditions where the stimulus being presented in the receptor field of this neuron was a particular stimulus of this neuron light. And liked it because it fired a lot of spikes when it was presented. That's what this shows. But the important thing is that after this stimulus was removed, during the delay period, nothing is on the screen. This neuron still fired at an elevated rate compared to when another stimulus was presented that the neuron did not operate. Right? So this is what we call persistent activity, selective persistent activity, cued persistent activity, and it's a fundamental phenomenon that has been linked to memory.
So then if you persistent activity, it means that the neural activity now is just relying on the certain attractor, and then the attractor is stable.
Yeah, that's what we're going to claim, that it's an interpretation of this. This is the data. This is the original on that. One way of getting here is through an attractor. That's a different thing. Yeah, this is the thing. This is a different. Okay, so this would be memory, as we're going to try to explain with these models. And the other one function, the main function that talk about is decision making, and there's another classic study where monkeys are trying to fixate, and then there are two options given at either side of fixation point, and stimulus is presented in the middle. Those are random dots, so dots that are moving randomly, but not quite randomly. Some of those dots might be showing coherent motion in one of the two directions, either to one of the dots of the response dots or the other of the response. This is presented for a while, for a given time, and after that, there comes a delay, and shorter or longer, and the monkey is supposed to tell us which of the two directions the monkey perceived a stronger motion in that direction. Okay, so that's the task the monkeys have to do. This is a a motion discrimination task. It's another classic, very important task in the field. The finding they reported in the posterior parietal cortex, and the finding was that neurons, some neurons in this area, would show this ramping activity that during the period in which the monkey is seeing those random motions that are not clear, right? So you have to picture this. Most of the dots are moving randomly. Just a few are moving in one direction. You have to pay that direction, whether it's left or right. And that's unclear. So you have to wait and calculate, or we call it accumulation of evidence. And during that period in which you're trying to figure out if it's more left or more right, we see these neurons sort of deliberating, ramping up when it's clearly to one side, and I'm not quite knowing where to go when it's nowhere. There's no actual motion direction in the stimulus, right? And this is a very influential result that shows that these neurons seem to. The crucial thing is that it depends on how strongly the stimulus, the coherence of the stimulus is. So when it's a very clear stimulus, these neurons know, they ramp very quickly. When it's a very unclear stimulus, even no signal in it, they don't seem to know. Although the finding was that actually, when the animals ended up saying to the right, these neurons seem to be sort of figuring like a right word, because there's this tiny bit of a right word. And when they were going, so it was another super influential result. Say, there's no motion of evidence in the stimulus, and yet these neurons seem to be driving what the monkey ends up doing, because they start going. And this is a fascinating body of work, but this is the sort of basic phenomenology that we're going to try to think about how models can do. Okay, so the first thing I want to see here, or reflect upon, is that for both of these basic functions, what we're looking at is something slow. So we need a system that is slow enough to the point that it's just static, right? So that you give some information and it stays there. This is what this is. Or it is a slow ramping that occurs in the scale of seconds.
The non-neural recording?
This is one, yeah.
But I think the behavior doesn't be alone.
Right, yeah, okay, we're not going to go. That was the whole discussion back in the days. So how could this be? There are a whole set of papers figuring out, and there are some correlations, just probably there's a lot of super exciting work being done on why. Actually, from a single neuron, the result was you do better than the monkey. So the neuron knows better, the monkey seems to be, so that was the result. Yeah. We can discuss about it. That's enough. Very good. Yeah, oh my God. So, okay, so slow. We need networks to be slow. Okay, that's a feature that is specific of cognition. If you think about what a brain is done, or the brains across all animals, this is not their main function. Right? So their main function is to escape from predators, to eat. Those are the main functions, and they're typically required to be quick. You need a system. Your brain needs to be super quick, so we survive. So that's a requirement. So all these things are not in the basic elements. The basic elements of the system, the neurons, definitely. They cannot do these things on their own. So neurons on their own, they have a short impulse. So that's what So they are not able to maintain things for a long time, and they're not able to integrate. And there's a good reason for that, because otherwise, we would be bad at escaping from our predators, and that's not good. The cognition comes later, and the later stage, the second order thing. First thing is big. So we have quick our basic elements are real quick. So then how could we get these functions to emerge? And the first idea, is okay, networks. So we just couple those very fast systems. We have a neuron that is fast, but now I'm going to be talking about populations of neurons. So I'm going to go into, I still have just one variable, but it represents a big population. So it's like an average family. So I'm going to be talking only about rate models. Everything I'm going to say would be taken to sliding in network models, but just as Yusho said, yeah, that's more advanced, and I think we can stay here for. So you have to think of this about like a population of neurons. They're fast, each of them, but they're coupled recurrently. So this population is exciting itself. Then the equation will be very, very simple. It's similar to the equation we're seeing yesterday. So that the rate of this population will evolve and will typically decay to zero, except that they are coupled to themselves. Right? If you just simulate this, and here you have two simulations that I ran. So, and on these simulations, this is a simulation of this system where all it happens, the inputs, that's what you're going to see in the number plot, is the inputs that are injected into the curve, into the system. This is just the delta function, a pulse. There's the pulse and the excitation. I have this population go up, and then yes, the rate goes up, but then quickly decays back down. That's the time constant. But if I couple, it's stronger and stronger, and that's what you can see here. As I couple the population more strongly with itself, eventually, so the dynamics becomes slower and slower. So there's a way of slowing down, and this is what we want for those functions. We want a more sluggish system. So this could be, and this is the basic mechanism that we always think when we think about how to get it into these more slowly functions. So recurrent excitation is fundamental. But as it was said yesterday, as we go beyond a certain threshold, and this is very fine-tuned, this would be when the coupling is equal to 1. When this is flat, as you can see, then we're flat. It's just a 0, so we are at a fixed point. But it is very fine-tuned. We cannot get there. And if we go beyond, then we start exploding. Right? So this is not a great system. It does achieve slowdown, but it's not good because it explodes easily, and it's very fine-tuned to really get to that burden environment. So that's enough. So how to solve this? And that's when people thought, okay, yeah, there was inhibition. Let's think about what are the players in this circuit. And the other player that we have that we didn't put in the previous model is inhibition. So let's put inhibition. So rather than say we're just adding stuff that we know about the system. So we're going to go to the bottom of it first. So now we put inhibition. And now we're thinking about cortex. And in cortex, the structure looks more or less like this. So excitatory populations do self-excite themselves, as we were mentioning before, but they are also excited inhibitory populations that feedback with inhibition onto this. Right? So this would be like the general thinking about what these circuits are built, how they are built. So this would be equations that we provide, and we wrote this equation in most of the Compte 1972, like these classic studies, and they were thinking about how does excitation inhibition interact, and they did this very simple mathematical model, super reflection. So again, we're thinking about populations, like in current rate, and they have couplings between the two of them. So here, this would be like the current that excitatory neurons get is like a coupling from excitatory neurons minus a coupling from inhibitory neurons. This minus this is a positive constant, so it's inhibited. Inhibitory neurons reduce the current, excitatory neurons increase the current that these populations sees. And the same thing at the other end, we can have constants. And then here in the Wilson column formulation, there's this other term that represents saturation in parameters. This is, and E and I, they are sigmoidal functions. And, yes?
Can there be a way from I to E? There's no way. Oh, yeah, there you go. Okay.
This is I to E, this is I. Yeah, sorry, this is I to E. Right? So blue is inhibition and red is excitation for us. So these are the equations that Wilson and Compte proposed, and now just mentioning I'm going to have different sort of equations as Yusho was saying yesterday. They are quite equivalent. Yeah, you're going to find maybe some stability differences when you play with that. But there's, and across the history of all these fields, several formulations have been used. And Wilson counting for this. Yes.
So the maximum current rate is equal to 1?
Yes. Here it's representing, yes, an abstract arbitrary unit. Okay, so then here's a simulation of this model. So I'm going to show you just a particular simulation. You can get the parameters and this is just showing, similar to before, for the previous simulation, all I'm doing is injecting a step current with the Attractor population and making it final. Right? That's what happens there. Now what you see is that the situation is different from before, or at least, well, we could get there by tuning J to be equal to 1. I get this stabilization, right? So they go into a steady state. They end up stabilizing with one parameter for the Attractor population, one for the inhibitor population. That stays forever. Okay, so this, we can play with, as we were doing before, with the coupling, right? In the previous slide, we're playing with the coupling. We saw it was very sensitive to that parameter. Here, if we play with the coupling, what you see is that, yeah, it does change. It goes, down or up. You see all those changes, but it's super stable, and I'm changing it by more than 20%. So this is really a much more stable system. This combination of inhibition achieves really a stabilization. The long time constant, the stable firing, something that the units themselves cannot do. They are fast. But the system, the network, is slow because of these very stable. It's a stable achievement. Okay, so this would be this EI network, Wilson column. Yeah, we can do math here, and there's been a lot done on math. You can visualize how this works by thinking about null points. And null points are essentially, so if we would like to find the steady states of these equations, what we would do is we would ask this derivative to be 0. That means we want to find points in which the rate doesn't change. The excitatory rate and the inhibitory rate. So we put a 0 here, and we try to find solutions that satisfy both of those equations at the same time. So one way of solving that mathematically is to write those two equations that we're looking for and then plot them independently one of the other. That's what we call null points. So in blue we have the E null point, the excitatory null point, in orange the inhibitory. And then the intersection of those two, where the two equations are satisfied at the same time. So those are the solutions of the system, those two solutions. And by looking at the flow, that's the velocity of those two derivatives at different points in the state space, you can see that some of these points are stable in the sense that all these lines point to them. So if you just depart a little bit, you're going to fall back down. So that's a stability. It's a stable point. Stable point. This is not a stable point because if you move a little bit away, boom, you're going to be taken elsewhere. Okay. So this is what we call the saddle node and stable node. Okay. So this is representing what went on over there, right? So there is so there are these 2 points. One is 0, 0. The two rates are at 0. If you get a pulse, you're going to be sent somewhere, and you're going to end up in the other fixed point where the two rates are non-zero and they stay there forever. These are the functions. These are these two functions. It's sigmoidal functions. These are the nonlinearity.
So it's a state space analysis. How is depending on the F function?
Depends totally, yeah. So if you change those functions, this will change. So you'll have to retune your parameters. Yeah. So you can play with all these. Yeah, I use this wave pipe package to do all these things analysis, which I just described for this talk is developed in Beijing, and it's very so you can. Okay, so the other tool we have, we'll look at this is, okay, now I have my fixed points, but then I can track the fixed points as I change another parameter. And that gives me a more, stronger, deeper insight into what goes on in the systems. In this case, because we're interested in the stability with respect to the strength of the excitatory connectivity. So I can change the excitatory connectivity on the x-axis and then move and look at how, as I change the excitatory connectivity on the x-axis, the fixed points change. So these curves will change, the intersections will change, and I can track these 3 points. And then you see here that we end up seeing like what we call a regime of stability. So there's a regime where for a given strength, you can be both in the 0, 0 in this state. This state is stable, and this one stable too. We are in that situation where you can be in one state or the other, and that's what we will be interested in that particular. Because if we are here, any pulse will take you somewhere, but you will fall back down. You don't have anywhere to go up here. So these can become, disappear, essentially. This disappears below a certain strength of connectivity. That makes sense, right? If you don't have strong enough connectivity, this is not self-sustaining. It's not going to be sustainable. So this sort of makes sense, and it helps us a lot when we play with these models to understand what's going on. I would recommend, if you're interested in this, to play and get used to the shapes of those bipartition diagrams. We call them bipartition. Okay, so this would be the Wilson power. This is one of the models. Let me go to another one. This is the education stabilizing network. It's the same. The same structure. You see the same drawing here. Equations are quite the same. I changed the function. Instead of being that f function, there's no saturation now. It's a linear threshold function. It's still non-linear. It's linear threshold. And now I give you another set of parameters, and that's what this network does. And that's quite interesting. So it does something similar. So again, there's a pulse that comes into the excitatory population. It goes away. And then this system stays on. You know, the interesting thing here is that it changed from a situation here where there's, this situation is the same as that, so in terms of units that the network is getting, and yet the network is splitting at 2 very different dynamic equations. So here, there's a fixed point 0, they're stable there, and here what we see are oscillations. So there's oscillatory dynamics going on there. So this is something I just want to mention. I want to drop here. I'm not going to go into this anymore, but these circuits have been used a lot to understand, get a sense of how oscillations are generated in vertical networks. So they very easily go into oscillatory dynamics, and that's interesting because oscillatory dynamics observe very much in recordings. So so it's easy to get oscillatory dynamics in the circuits when we have excitation and inhibition interacting, because they have different time constants. So excitation tends to be slower than inhibition. And that brings, the other way around, excitation is faster than inhibition, and that brings you through these things. Okay, so I'm not going to go more into that. Just to show here what happens in these other regimes, different regime, I'm going to show you exactly one specific difference that makes them very nice to compare. But here, let me just show that, again, as we change the coupling, we get stability, so we can make that coupling stronger. It doesn't change much. It still maintains that elevated state. And then if I make it weaker, at some point it's going to stop. Right? At some point, that elevated state stops. So it's not able to maintain that information. That information goes away. So we again are in that situation where we need strong enough recurrent coupling to get into that state of elevated activity. Yes.
So we change the nonlinear problem, but previously it's nonlinear, now it's rule.
Yeah.
Then we can have limit cycle.
Right, but that's not I'm not sure, but that's not, there are several changes here. I'm going to show you, why don't you go to the next one, and maybe, so let me show the state analysis for this one. So for this one, when we use when we plot the nullines, the nullines, of course, now they're piecewise linear because of the threshold limit function. But the crucial thing really is that the intersection is with the excitatory nullline shallower than the inhibitory. And that this, the fact that this is the intersection has this particular relationship in their slopes, that's what generates these interesting dynamics. You see here the oscillatory dynamics along the point. In this case, it's a focus, meaning that it converges into an exponent eventually. And again, yeah, we can do the same dynamic with the same bifurcation diagram to try to see, how stable this is and what is the range in which I can change my parameters and still stay at the regime I'm interested
Which so formal resting goes forward to saturation is not percentage.
Yeah, that's another feature. You could be, yeah, I don't know if you could get this regime with the saturation. I cannot. So there are several things that I don't think that is critical, but it indeed. So Wilson-Cowan classical has a saturation term. This doesn't have. I don't think that's crucial, but it would be worth exploring. Okay, so let me show you what is.
Sure, refers to the EQ.
I only played it up. Yeah, yeah, you're right. So you could ask other, or you could put our parameters here. You have the code, so you can play it. You can just change them and see. Okay, what about inhibition? What does inhibition do to this thing? Well, it's just one line of code. Change it, and you're gonna see. I only wanted to show you, this particular manipulation, because I'm emphasizing here the robustness of excitatory and inhibitory networks to maintain these stable states. Okay, so so now I'm comparing the two. Wilson-Cowan, several differences here, right? Division stabilizing. But one thing that we noticed, and it was already back in 1997, was that there's a crucial difference that is quite remarkable. And it's a bit of a peculiarity. So suppose now we go into these stable states. Now I changed a bit this parameter, so there's no oscillations. I can see things more clearly. And now I'm going to put a stimulus here, and I can excite a pulse going to the excitatory or to the inhibitory population. Just a pulse. So I'm going to send and make one of the two fire more for a short while, and then see what happens. Okay, so if I put this. There. Okay, something. Okay, so yeah, I put the stimulus in the excitatory population. I should have excitatory rate goes up, inhibitory rate goes up. So it makes sense. Nothing, it's our linear thinking that said this would have happened. What if we stimulate the inhibitory population? Well, I stimulate the inhibitory population. The inhibitory neurons increase their rates. Makes sense. Excitatory neurons reduce their rates. Makes sense, right? If you think about recurrence. This sort of makes sense. But now we go to the other one. We excite excitatory neurons. And excitatory neurons go up. But inhibitory neurons, big time, super strong, should go up. This is very different from what we have here. Excitatory neurons go up. Inhibitory, they're not getting any input, right? So they're just getting the drive from the excitatory. Here, the one that really responds to the pulse of excitatory neurons are the inhibitory. That's one peculiarity. But then this is even more striking, which is we send a pulse of excitation to the inhibitory population. And the inhibitory population goes down big time. We're sending excitation, but it goes down. Okay, so the response of an excitatory pulse to the inhibitory is actually a reduction in the fire rate of the inhibitor. In that report, not in this one. I think I compared the two reactions are totally different. Yet the system is exactly the same, except for this. There are some differences in the functions and the parameters, but we are qualitatively different. And this was brought up, so it was first proposed or shown in this paper, and then brought up again in this other article by the Miller Lab, and this was very influential because suddenly we had the tools to test this. So here, so let me skip this. So that you can interpret that. Why is that happening in terms of those null lines and how they change with the pulse? Yeah, I'm running late, so let me skip that and just go to the data. So that the fact that we have those two contrasting predictions between two single models, that suddenly someone realized, well, we can test that. We have the tools. So all we have to do is to excite the coordinates in the recurrent circle and see whether there is correlation with that. So this can be done today. It couldn't be done 20 years ago. So in a mouse model, they recorded in several areas that we published in one, and they also had a virus that I don't know exactly how they did it. There was this offset in the inhibitor neurons, so that when they chime by, this inhibitor neurons will, drive the inhibitor. Supposedly, they increase the power. But when they look at the physiology, when the light is flashed, you get that initial surge rate, quickly they go down. So the rates go down. But it's a secondary cost that is being applied to the inhibitor. So it's really, this was meant to test specifically that prediction of the model, contrasting these two regions. And what the data shows us, quite convincingly, at least with V1, is that the system that seems to be between these two options would be thinking more of this regime of operation, where the inhibitors have this very steep gain in their function, in their response function. Okay. So this is one example of how, from these very simple models, very cool experiments came out that were able to talk about two conditions that.
So in this instance, D1, people think that the D1 network is in the highest and medium, or there's still debate.
I think it's 1/7. Yeah, at least for sensory cortices, this would be the case. I think for more, more forward in the hierarchy, it's not as clear. There are others. So this is like a more direct test. There are other tests where we can look at contrasting variants and different features of the visual focus responses that seem to be more with the patients than the Okay, so now let me go to memory. So this was like this basic network function, excited inhibitor. Now we're going to go into permission. I remind you that this was the problem, how to stabilize a memory and into that context, we presented this to the animal, and it had to be maintained in memory. And as we're saying, Attractor seemed to be a natural way. This would be the other paradigm that I'm going to be presenting later as experimental observation of some of the prediction of the model. And this is a work from the Swoboda lab where animals that are nice, they hear a sound, one or another sound. One sound means lick left, the other sound means lick right. But between the sound and the response, there's a delay. They have to maintain memory which are the two sides they have to lick on. And during that delay, neurons show something like this, elevated parameter for one of the options and not for the other option. Okay, so just similar design as this one, but in the mouse it's going to give us a little bit of frequency. It's cool. Okay, so how do we go about modeling this? So people thought about this and they said, well, it's a bottom up. What could it be? Possibly there are two groups of neurons, E1 and E2, each one representing an option. So lick left and lick right, for instance. And then they're controlled by inhibition, because that's the general theme in the cortex that seems to stabilize. Then, if you just go, as we were going before, through the possible equations of this circuit, so we're going to have to do decay. Now, see, I changed to the other formulation that we were seeing yesterday, where now instead of the rates, we have the currents. but that's all right. Sort of equivalent. This is more, this is how, you know, more modern formulation maybe. And then, yeah, you see, you couple, like, so you convert currents to rates through the Attractor, and then you build your current depending on the excitation and inhibition that each of the populations sees. Okay, so these are three system equations. That's a bit annoying to deal with, and mathematically we like two equations. So, you know, there's a way of reducing 3 to 2 by assuming that that inhibitor population is just there controlling things. It's fast, so it's going to adapt. So what we do is we put a 0 here. We say the inhibitor populations are just adapt instantaneously to the condition. So we put a 0 here. We solve this for the excitatory rates of currents, and we put that back in. And then we can end up just caring about the dynamics of the two populations. And the result is that effectively these two populations are like exciting them with each one, equally. You know, recurrently each one of them, but then across what we see is inhibition. And this could be the basis of these networks where we have weights that are positive and negative coming from the same neuron. You have to think this as an effective connectivity, possibly involving the intervening inhibitory populations. And that's what you can work out with this simple this. So the key genes here. This is non-linear. Well, that's key. It's key there. All these are non-linear. Absolutely. Okay, so then we end up with this formulation. We have an excitatory weight and inhibitory weight for this effectively, inhibitorily, interacting recurrent excitation system. And this has been very well. Right, that's 1, 2, 6. So okay, let's look at a simulation. So what we can do is do the same thing as before. I can inject a pulse of current into the excitatory population of 1. And what I see is that when I put that, it goes up, but then it stays up. And the other population, it goes to 0. And if I do, of course, it's symmetric, right? So if I do it on the other one, it's the reverse. Okay, so that's nice. That's this, that means when my system, so the system is happily there, waiting, and then when some very clear stimulus comes in, so the liquid left, it's gonna put one of the populations in one of the states, and then you can wait there for the delivery as long as you want. Whenever the instruction response comes, you are in a position to say, okay. Right, so the delay is not an issue anymore. There's memory in the system. The memory is telling you what happened, what stimulus appeared, and it's no longer there. Okay, so this is a system that can do that. Okay, so how do we think about this? Okay, one way of thinking about this that is very useful and we use it a lot is to visualize this as an energy landscape where there's a ball falling down. So in this landscape, we're going to have the time rays of the two populations exciting the one of the two population. And then here is like this energy. It can be computed for this system. Not all systems allow an energy formulation, but if the connectivity is symmetric, you can derive it. Here you can derive it analytically, and I just plotted it here for that particular system. And here you can see the so you can visualize this. So this would be like the energy landscape for this particular system with those particular parameters. If you change the parameters, this figure will change. And then you can, here you're seeing so here you get like a slow manifold. You see that this is almost flat down here. So that means that's where it's going to be slow. The system in that area, when the rate of the population 2 is 0.2 and the rate of the population 1 is also 0.2, it's going to be in this region. It's going to be there slowly, but this is not totally flat. So there's dynamics there. Indeed, if you look, so there's like a deeper well here and a deeper well here. So there are deeper wells. So then this means that if you put a ball here, it's going to go very quickly down to the slow manifold, but then move to one of those two wells. You can look at this from above, and you see those wells here and here. Those are the steady states. So the system, if you wait long enough, it's going to go straight to this, and then that's the dynamics of the system. And it's useful to visualize it this way, and we do that a lot. Again, you can think of the system with an outlines. You can plot an outlines and intersections that tells you that there are 3 stable states. One where the 2 populations fire at low rates, one where 1 population fires at high rate and the other remains at 0, and another one where 1 population fires the other population fires at high rate. You can track those as we change one parameter, and here one interesting parameter to think of is drive, which is like an overall drive to the system. That's interesting because that's something that you can think about other areas doing manipulation. So there could be a modulatory input that's just a drive. So a drive from another area can control how this area responds to the stimuli in a way that it can be here, where there's only one thing this area will do. It will only be in this state here with low rates for the populations. You can put stuff in, it's going to represent it, but the minute you take it out, it's going to take it back. So this is more of a sensory regime. This will be a fast system. But now this area gets a drive from another area, and it's turned into something totally different. You put it here in this regime, now the drive went from this value to that value. That's, we have to assume another area to it. Now this area, suddenly it has a super strong, super slow dynamics so that it can stabilize one individual drive that's transient, comes in, goes away, and boom, now it stays there forever. So you get memory. But this system, you see, can do sensory and memory. You can control whether this system goes into a more fast, quick response regime or into a more sluggish memory regime, just by changing drive. So this is an interesting way of thinking about how memory and how would emerge in a way that is not, you don't dedicate this area just to that. And the other interesting thing here is that you are in what we call a multi-stable regime, where you can be here in this one, this state there where both rates are low, or in the other ones, without changing anything. You're there sitting, and you can be remembering one, remembering the other, or not remembering. And that's interesting. That's the regime. Since I started in the field, when I was postdoc Chapman, we would always want to be. So my postdoc years spent fine-tuning parameters. So I was here always. It's what we think. It's the way in which this system is more independent. It can do anything. It can do no memory. It can do memory, and it doesn't need another area to tell it to do one thing or the other. And that's interesting, but it's not the only solution.
One thing. So I see the drive x-axis label as an active value. Does that mean that you can get storing drive to the
yeah, true. No. I mean, the way I was presenting this drive from another area should be right. So you could just think that there's another, my thresholds in my neuron should be set so that it's not. So think of it as it's growing. So the absolute value of this doesn't really make this very toy example.
So with that, the dynamics is drawn on the fixed and then the surface.
Yeah.
Away, and then the dynamics is operating.
So
the dynamics is operating part.
Yeah.
Then it's fine.
Yeah.
This can be verified by the marking.
Yeah. You mean if it goes very fast?
Yeah, because all the so checking the dynamics. So it's a low point.
I'll come to the experiments. Yeah.
to take a break?
Let me just finish this network, then I'll take a break. Okay, so I was saying that these three stable states, that's interesting, but it's not the necessary situations. Here's another one. So here I can put stimulus 1, it does the thing, stimulus 2, it also does the thing. It remembers, but you see that before that, here in this part, it wasn't stable, right? So we don't have that stability. This is the diagram. So there are only two fixed points where we have selectivity. One rate is high, the other is low. One rate is high, the other is low. So they remember one of the two options, but we don't have the middle one is unstable. So we don't have a solution where both are equal, right? So this is there are only two options available in this way. It still can do the task, but then it needs another. That's what I'm representing here. Then it needs that one area is telling you nothing to remember, something to remember. Nothing to remember, something to remember. When there's something to remember, whatever comes in will decide whether to go into one or the other. But you still need some other area to be in control of what this area does. This area is able to selectively store one of the two, but not to decide when it's time to remember. Because if you're here, you're gonna hallucinate. Even if nothing is there, it's gonna have to go to one of the two options. And then this would be like the diagram of what goes on. In this regime, there's a stimulus coming in for one of the two options. That option goes up, but it quickly decays. Because we are here. We are in this side. It doesn't remember. But then there is this drive up here that says, okay, time to remember. A drive coming to total population goes up. And then now we are in this. And now the same pulse applied at that point, it is stabilized. Before that, it starts deciding. Because it cannot stay, right? So the minute you go here, this becomes unstable. So it's going to start there. But any pulse will correct and send you to the right location. So this would work as another system of network, but it requires another area that's sending this input that knows when to memorize things. That's why we didn't like it back in the days. But we have these two options. And I guess experiments with helps. We use the right. And yeah, there have been experiments. And right now the idea is that it's more the right, which asks the question, so which is the area that's pushing us? So we sort of find areas that behave like this, but we don't know what area is doing the job. So let me show just the evidence before we break. The evidence for that comes from, especially the work from Svoboda. And this was the experiment I told you about. Mice in this auditory task, movement the waves. It's a motor preparation task. During this motor preparation period, there was this elevated activity that's separated, that is different in ALM. This is ALM, imperial lateral motor cortex. And yeah, what we did is optogenetics, right? So you can do optogenetics. What we said is, okay, here's the thing. If those are our two options, and we are memorizing something, and now here comes genetics, and it perturbs me. Well, the next stable state, perturbing means, fluctuation on one of these y-axis, and then it might, if it's strong enough, it send me over this hill, over this valley, this ridge here, saddle node, and boom, you're going to fall to the other end and fall to the next stable state. So a perturbation should send you from this selective state, where one is winning over the other, to the state where the two are equal. The other state is too far, right? So it needs to. So before perturbations here should primarily send the system to a case where, I don't know which of the two options you are in this state, in this equal represents. Instead here, if you are representing one thing and one of the options, and the perturbation comes, you're going to go over the saddle and fall into the other option. So you're going to represent the other option, not the case where you don't know. Right? So that's the different prediction these two regimes. Here, perturbations from a case where the system knows which other two options is presented. The perturbation sends you to the two populations have the same rate. They don't know which one. So you forgot. This is more perturbation should be forgetting. And here, perturbation is to a convinced sense that it's the other option. Does that make sense? So those are the predictions that those two models made that can be tested experimentally. Yeah, that's what they did. So they they perturb with a limited ALM during the delay period when supposedly the system is sitting in one of the steady states representing two options. Well, one of the options. And what they see is that when they release the incorrect trials, well, the response goes by. That's okay. That means the perturbation was not strong enough to send you over the saddle. You remain at the same place where you were, and you recover. So the dashed line is what the activity was before, without any perturbation. And then the solid line is the activity with the perturbation. You see that it converges to the same state after the perturbation. That means it relaxes back. So you perturb, if it's not strong enough because these were correct trials, then the activity relaxes back to what you have laid without perturbation. But here's the interesting part: when you look at the incorrect trials, when the mouse was supposed to lick left and lick right, so it could be that it licked wrong because it just didn't know that it licked wrong. And then you would expect that the two lines would be equal. So there's the two firing rates are equal, meaning that the animal doesn't know. You are in the middle state, that state of equal rates. But instead, what you see is that, boom, they flip and they go to the other steady state. It's like the perturbation when you go over the saddle. It doesn't take you to the equal rate solution. It takes you to the flipped solution. Okay, so that's what that's the interpretation of these results, and that seems to favor that other, so that second option that I was telling you. And yes.
I think this is not scientifically regulatory policy of the or the whole population of neuron that informing this problem. If only you select a small population, you don't never know what will happen if you perturb more. Right? What if this ramping as a consequence of that, the remaining active neurons encoding the evidence activates?
Well, yeah, that you can say for this side, right? Not for that side. So here, if you're not inactivating sufficiently the system, then yeah, the rest that you're not activating, inactivating, the rest can be recruiting you back. That's what this shows. But here, you're flipping. So suddenly what the rest are telling you to do is the reverse of what you should have done.
What if the observation is strong enough to cross the critical points? How do you know that you're doing best?
Yeah, I don't know. Yeah, you could do it better. It's pretty convincing. We thought it was pretty convincing. It's the first time we will be testing like this perturbation, ideal perturbation model. We've got, but yeah, I guess you could be more selective as to try to perturb only one of the two populations. Here, it's not selective, right? So you are inhibiting the all of the neurons, not only the neurons that are performing one of the options. So you could be more selective in the way that there could be more specific manipulations. Right now the tools are there. This is a not so specific. But yeah, the interpretations go in the direction. Yeah, okay, so I'm gonna skip to my last. This was my own work, also in that direction, but I'm gonna skip it.
These two applications just you prefer for the English language or the just for the Finland? Like what is the subscription with the picture? You said that the behavior
no, it would be generally true. It's thing. I mean, maybe you can find. So if you think about in that diagram, it was clear that thinking about the disturbance, right? So really, it was very hard to get from 1 to 2 directly because there was this huge hit on the middle. But it's true that maybe you can tune things so that it's not that. I cannot say if it's that. We didn't have mathematics. Anyway, let's break here and have a break.
All right, let's start.
So yeah, sorry about you were interested in decision making, but we not spoke on that. It's essentially the same circuit. So the same circuit I already mentioned when the drive puts you in that regime where you're forced to take a choice because the neutral point is no longer stable. Then that's a situation for decision, right? That's the case. And that's how the same circuit we're talking about, you can think of it in the context of decision making, and it takes decision because a drive puts you in a situation where the equal rate condition is no longer stable. Then the circuit will take a decision for you, even if there's no evidence. And that's how these circuits have been shown to relate very closely to the phenomenology of that past that I was mentioning before. So, I'm sorry, but I'll skip over that. It's the same model. You'll have the slides. It's evidence. I mean, also some perturbation experiments with microelectrode experiments. But then let me go to the last one. So this is continuous spatial memory. It's very dear to me. That's working on this model. So let me tell you about the tasks that we're going to think. So these are monkeys. This is a classic task. Was developed in the lab of Richard Goldman Repeach at the Yale University. This is a famous paper we've actually about in 1989. Monkeys were trained to fixate then one key appeared peripherally in one of 8 possible locations. Then there was a delay where the monkeys had to keep in mind that location of had been presented on the screen. And then at some point there's a response. So monkeys are asked to tell us where was that stimulus. And they move their eyes and they fixate on one point on the screen, and that tells us where they remember that location. And then that's the response. In this case, this is an error, right? So the monkey says it was here, and it actually was there. So this would be an error for this in this track. These monkeys keep doing this. So the important part again is the delay here, where they're memorized, keep it in mind. Where location is. And now this is somewhat different. I mean, you could say, oh, 8 locations, all they need is 8 populations instead of 2, right? It's not left, right? It's east, west, northeast, northwest. You could have 8 populations that you could build that model. That would be a possible model, and it would work. But it would have it would miss one important feature of this test, and it's that there's a topology, the power integrated topology, right? So yeah, there are some views that are close and some that are far. And monkeys, can make errors to the closure of that more than far. So, sorry, before I go there. So this would be the physiology that they get. This is in the prefrontal cortex. These are recordings done in the prefrontal cortex. And this would be one neuron recorded there. Super beautiful neuron, one of the most famous neurons in neuroscience, I would say. And this one neuron particularly like items that were presented at 70 degrees south. So these are like all the responses of these neurons when we, so all the trials are presented with stimulated communications all the time, but then when we analyze the data, we put them in this organized way. So all the trials in which the stimulus was presented in 70 or last year, all the times where all the trials in which the stimulus was presented in 35 or last there, and so on. And what you see in the first stimulus by histogram, so when we accumulate the histograms about that activity, is that during the Q period, when the stimulus on the screen is the C, there is some responses, but the important part is what happens in the delay. When there's nothing on the screen, well, this neuron's not, right? So this neuron had a clear idea that during the delay period, when the stimulus has been presented at around 70 degrees, this neuron is super excited, keeps firing. But instead, if another trial is presented just a little further away, it's not at all interesting. So yeah, there's this selectivity, this persistent selective activity In this case, we don't see too much about this topology, but saying that there are other neurons where you see that it's also graded as you get further away. So this is high, this is middle, right? You can see those neurons. Anyway, so this would be like the phenomenology, and what is the model that has been proposed for this? I mean, it's a model that we still use a lot. And it has a tremendous power to explain many of the phenomenology of physiology and behavior in these places. So what we think is, okay, we have neurons, but now instead of having two populations for two options, we have a continuous of options. So all my neurons are set on the brain, and we can have like hundreds of neurons, each one at a different degree. I mean, you have to picture this as a true implementation in the brain. It's like an abstraction of how they are disposed in this representational space. In the true physical situation, they can be totally scrambled. So assume we have these neurons on the brain, and then we connect them in a specific way. This little ad hoc, we do it in my hand. And we say neurons that are more closely together, that means they're going to be getting stimuli from stimulus in more or less the same area in the visual space. They're going to be more strongly connected than neurons that are further away. That was this of my errors. And then there's inhibition. We're going to think for simplicity in about just a global inhibition. So this would be like the equation to this. Now this, you have to think, you have n neurons, so that's the subscript I, can go from typically hundreds. So there are many equations here, it's not only two equations. And we have all those neurons are coupled within one another through kernel IJ, so this is very similar to the RNNs that we were seeing yesterday. And there's excitation and inhibition. Inhibition is global. There's only one population that gets excitation from all excited neurons and feedbacks to all of them. And then we have to assume this translationally invariant selective coupling that, for simplicity, I'm going to put it close. So if we do this, that network will do what we want, but again, for simplicity, we can do we can simplify this by assuming that inhibitory neurons are very fast, they converge very quickly to their inputs. So essentially, we set this equal to 0, so Ri can be derived from this equation, and we can fit it up there. And then we get only one system of equations for the excited version. So only the excited population is considered, not the couplings are both excitatory and inhibitory. So we're going to be predominantly excitatory for neighboring neurons and more inhibitory for far. Okay, that's how this system, simplified system works, and that's what I'm simulating. Yeah, so we have to assume that the inhibitory population is working in its linear region. So that's an assumption. Which is, yeah, because inhibitory neurons fire at high rates, it works. So that's the assumption. And that's this gamma. So that gamma here is the slope of the derivative of the function at the
yeah, why do we specify the exact form for the EE, for the EE and the other, for example, IE, II, and the EI, you never specify the.
Sorry, it's not clear. Maybe I should have put IJ over there. So this one has 10 parameters, right? So it's a big matrix, and these are only statements.
Oh, thank you. But it is a constant.
These three are constant, but this is not. This here, that's why we use this specifies. So then now this also has one constant.
This form is just really like the form of the Raman model. Remember? Raman model is cosine of sigma minus sigma. It's really like the form of the quantum.
Right. No, but that's.
So this is a guess, right?
Huh?
How do you choose this calculation?
So this is the coupling between them.
Yeah. Why do you choose the cosine function?
Oh, because I want to have this symmetry and this feature that neurons more close to one another. So theta I and theta J are labeling where the neuron is on this ring. So if two neurons are very close, cosine of 0 is 1, this is J. If two neurons are very far, the cosine of that will be -1, this will reverse.
But what is the point?
It's a total thing, yeah, we could put a Gaussian.
It never conform by
If it's a cosine, no. This is just the point.
But it's like with with higher,
Yeah, very
frequent, higher frequency.
higher
So it's like.
so it's like
Yeah, and the fly has found a system like this, and they're being number. Yeah, so this is really just to make it super simple. Actually, by using this, you can do Fourier analysis here, and this becomes, you can turn this series of this system of equations into just one equation, two equations for zero moment and the first moment. So that's why we use skills. So you can end up doing really lots of analysis and mathematical. Yeah, the brain doesn't. Okay, so this would be a, let me just show you some simulations run with this network where we inject a stimulus at different locations, so different neurons get the input. And then those neurons, once the input goes away, they maintain it because they're more strongly coupled. Right? So because of that process. Everybody is more strongly coupled to the neighbor. So those neurons that get the initial excitation will be up and will be sustaining one another for the duration of the loop. So this is a bit complicated. This would be like the pattern of activity at the end. So that's possibly the readout. So how do you read out from this network behavior? So behavior would be the magenta line. So this line over here is like getting the center of the activity of this circuit through time, like what is it representing? And then when the stimulus comes in, it stays there, meaning it has a clear idea of what is the angle that is being stored. And you can, at the end, just get it, and it typically goes very well with the red line, which is what they put in here. So the red line is what goes in, the purple is what is instantaneously being stored, and this purple arrow is what gets right out. So from this network, you can get behavior, you can get physiology, and you can compare.
Just two things. Where is the noise coming from?
The noise is additive. It's additive noise.
So you just have it
Gaussian white noise.
And how come it's so narrow with the phone?
Oh, because of inhibition. Yeah, it's not.
No, but it's threshold is what.
It's threshold, but this is zero.
But the amplitude should be some. Can you have arbitrarily large amplitude and arbitrarily narrow?
You can go very narrow. Yeah, this is low amplitude. Yeah, I don't know. 80%.
No.
Yeah. So anyway, this is like the sort of function you can get from this network, and that is, you would get activity from this, and you think about this as neurons. So you get a similar pattern to what has been seen in the prefrontal. Neuron like this neuron over here. So let's take the neuron at 0. With this neuron at 0 now, when the stimulus is over there, it's sort of active, but if the stimulus moves at 0, it's going to be super active, and then it would have that pattern of activity that we saw in the frontal. So collapsing in many trials, if the stimulus at 0, the neuron at 0 would be all the time very active. If you put the stimulus at -100, the bump would be here, and the neuron at 0 would not be active.
So what's the meaning?
Beep is the echo. So it's just getting the center of mass.
But then how come we don't see the phone?
Here.
Yeah. Yeah.
So there's, because
Because it's lower. It's just
yeah, this should be all over the
It's
yeah, you're right. This should be all over the place, isn't it? See, it varies. Yeah, tends to. Yeah.
Because it should be blue, right? Also be forward.
No. The color, it doesn't say anything.
No, but you have drifting bump, right?
Drifting bump is from here on.
No, but before you have the center of mass.
Yeah, the center of mass is just given the activity. What is the center of
So you
mass?
have no bump.
There's no bump. There's no bump.
There's no spontaneous bump.
There's no spontaneous. Yeah, this is this stable regime, this regime where the flat solution is stable.
But how come the bump survives afterwards?
Yeah.
No, but it's not it has to stay. It has to be okay. I think the bump survives later on. Yeah.
That's what I was telling you the previous time. So you can be in that regime. You can be the regime where a bomb needs to be there no matter what. Or you can be the regime where the equal activity is stable.
But can you be in a regime where both and the bump?
Right. Yeah. That's all my program. It was, fine. It's a narrow regime. It's hard to get. It's fine-tuned. We get there. And all our papers are about that because now the data seems to show that we didn't need to do that. Probably there's not really.
The question is, in this very high model, right, there are several variations of this. You can show one version, other versions, so it's getting close to data, is about you get 15. Rather than
This is a division.
I know that yeah, you'll still get you can hold that data I find.
I mean, the two division.
There's several variation of this. So experimentally, they can test which version is more favorable than others, or it doesn't really matter at the end of the day.
I think at the level I'm talking to, it doesn't really matter because we're super schematic. But yeah, if you want to be specific as to what it is inhibitory, are inhibitory neurons too? In this model, they're not. Right? Because they get flat excitation and they project flat inhibition. So there's just one inhibitory population. But in reality, when we have looked at it's inhibitory with Gomara Peach, they looked at their data and past active neurons, presumably inhibitory neurons, they are tuned. So then this is not plausible. So this should be tuned. Yeah, so it's an experimental question that explained permanently in models based on experiments.
So just one question. In this comparing where both the zero and the bump are stable, what's the unstable management? You have to have an unstable
Well, it's another. There's a saddle that where there's some say.
No, I understand, but what's the form of that? The unstable.
Yeah, I think so.
So what?
Yeah, it's a bump. So you see it go and then it decays, and at some point. Yeah, it's another bump.
And so you would spend a long time in the years.
No, it slows down near the fixed. That's quite slow.
We could go like in the prime or maybe both to the different quarters. Where
If you're close to the
where
bifurcation, yeah, then you can lose. Yes. Yeah, but that's here. This one is in that regime. So we have high stability, multi-stability with also flat condition. Okay, so let me run many of those. So now this is like, so I'm just now plugging into this middle click and forget about this part. Just plugging this magenta line for multiple simulations. I'm running multiple simulations. We're going to stimuli at different locations. And then you see, this is just showing, I also have the three stimulus. Three stimulus have a second, and then all the delay. Each color is one different simulation, just dragging the center mass of the bump. And what you see is that they do memory, right? So they do parametric memory in the sense that it's not often remembering a function. It's remembering the continuous at the end of the simulation. So that's the point of this model. We're able to store
So, we check like broader needs to be like near trade protection point or here it's very stable, right?
Okay, so if you look at one of, if you just go into one of that, so now these are a number of simulations I'm zooming in, the y-axis is no longer full circle, it's only 40 degrees, and now presenting the same stimulus on and on and on. Well, the different simulations actually fuse. There's this diffusion of these traces of the center of mass of the that is something that back postdoc estimated, and later we've been able to test it. And this is what one of the other experimental ways. So we went to go and test it and say, well, how could we test possibilities? And you know, the multi-electrode recordings that we now have available make it possible. So indeed, this is behavior of monkeys in this task. When we plot where they ended up telling us that they remember each of the 4 baseball patients, and as you see, they're not perfectly centered. There's like this diffusion, there's this dispersion around the targets. If you look in time that's been done in humans, for different delay durations, this grows. So there's more and more, which is consistent with this view over here. So the longer you wait, the more of that diffusion. So then what we've been doing is correlating neural recordings with those trial smaller errors that animals make. So here in these 2 papers, is just a what we do is in each trial we get how much the monkey actually responded clockwise or counterclockwise from the target. And these are minor, we're talking about a few degrees away from the target point. They're just because they're pretty good in the past. But they're slightly more off in one direction or the other. And then that is what we analyze and what we do from the neurons, because these are multiple neurons work simultaneously, is to decode what angle they're representing in neurons. And then we decode that angle that they represent with these dispersions of the monkeys. And what we see is that there's a correlation that builds up through the delay all the way to the response time. That is telling us that the predictions of the network of neurons are cumulatively predicting the behavior, the small diffusions in the behavior that we see in the monkeys. So it goes, so these diffusive dynamics that the model predicts is actually a good way of understanding how activity in the prefrontal cortex is evolving through the way to eventually generate an action. Yeah. So yeah, so this would be like evidence of that accumulating diffusion happening in this subpopulation or population of the frontal neurons that are reported during this test. Does that make sense? That's yeah. So what is time by time is the neural decoder. That is time by time.
In relation to the final.
To the final, exactly.
And if you just do binary, so left and right, instead of doing the related coefficient, you get something stronger.
Yeah, so we have it in that way. So is it stronger? Yeah, I think it's not as gradual, so we were more happy with this one. So in the first paper, we did this, just a handful of neurons, and we had to do all these, there are many different ways of looking at it. Also correlation between neurons. Neurons should be correlated, the bump, you can think about your neurons, depending on the neurons you pick. If the bump moves this way, one neuron goes up, the other down. Or, you have anti-correlations that are specifically predictive. You can check that and you'll also see it. So there's a bunch of predictions of these dynamics that you can test in the data. This is the new one that we did with multi-electrode. So yeah, there are several ways of looking at it. It's consistent. We've seen it. I think it's so anyway. Anyway, I have 10 minutes. So I concluded this series of basic circuit mechanisms for various things. One was more of the cortical dynamics. Yeah, networks and level 1 networks. I looked at selectable memory and two items. with last week, right? Linear decision making, that's an exercise. And now ring effector. I mean, to conclude, what I want to now think of is, how does this relate to this newer approach of RNA? If you think about RNAs, we're talking about the same equation. Right? So this would be the RNA equation we saw yesterday. And this is the equation that I have for my couplings. If I look at it the way we look at the matrices of couplings in sparse networks, it looks like this. I will get, this is what this connectivity looks like. Okay, makes sense, right? It's a different equation. And that's for that one network. So we can view this network as exactly in this formulation with this matrix of connectivity. And same thing with the other, these two item memory that we're talking about, with left and right. We can think of it like this other matrix, right? So instead of two populations, now I mean just two single equations, now we're going to have a bunch of equations for the populations, that's essentially the same thing. And this would be the matrix that would correspond to that one model, and we would, it's essentially the same thing. So this is just a change of perspective. But what if we do a rank one, random recurring network? So this, now we're going to go into this sparse matrix formulation. So let's assume, and we're going to do this, the rule is quite simple. So we're assuming, so psi is this, it's a random vector, normally distributed, independently drawn each of the components. And then we build the connectivity this way. So there is a very small assumption. There is more of like a field view, where we're assuming it's a sort of heavy learning, if you want to think of it. Neurons that are, so if you think of psi, we're going to think of psi as defining the selectivity of my neurons, right? So psi being positive and strong means that neuron votes for one option, psi being strong and negative, the other option. Then when you do this coupling, the positive side, the two neurons that have similar strong coupling, they're going to be strong coupled, and similar strong negative will also be strong coupled. So you'll get positive strong between the two extremes, and something indeed. If you just take this one random matrix, coupled this way, and now we reorder all of the neurons according to their rank in their value in that vector, which is this selectivity, then that same matrix looks like this. So we have a cluster of strongly coupled neurons in one extreme that are interacting inhibitorily with one another. Okay, so this is reminds us of that. Yes, just normally distributed. And this in the Python notebook. So every time I run I render my presentation, it's a new map. So I don't know what's going to come next. Okay, so it's really what I want to say is that this is robust. It's not just one time thing. Okay. So this reminds us of this, right? And indeed, if you do dynamics on that one, right? So this would be now doing dynamics on that switch. And essentially, so let me remind you. So I'm going to enter some. I'm going to treat this now random network. I didn't build anything into it other than the rank one. And having these couplings. And now I'm going to inject a current that's going to be selected, right? So it happens at this time, and then it affects that subset of neurons. So neurons, remember, they're ordered by how strong their loading is on that side vector. So these are the more negatively loaded neurons, these more positively loaded neurons. I'm going to inject current to the more negatively loaded neurons for the simulation. And what you see is that, well, I inject current between 1 and 1.5, and then they stay on, right? So that I have a memory for one of these two extremes. And if I run this for random or different simulations in which I inject at different times, sometimes I put the signals in one side or in the other, well, the circuit will store one side. So it's doing really very much the same thing that our our two-option discrete working memory system was good. Now this I didn't build bottom the way I did before, citation and efficient and two populations. This was built with a random vector that is only it builds this Hopfield-like connectivity with multiply. But it's super general, so you see every time you run it, you get the same. So you don't need to specify a particular. So yeah, this shows, you know, there's something more general about those toy models that we put instead. Not only that, but now we go to random. So now we take two vectors. So all two vectors are randomly drawn from a Gaussian, totally independent of one another. Of course, because of this high dimensional, they're going to be orthogonal. And then we build this matrix. So it's similarly, you know, it's again assuming a sort of ambient learning in that connectivity. And we sum those two. Again, it looks very random. But we can do it by order too. So now we reorder that those two vectors. By using those two vectors, we reorder neurons. What we do is we take this like a complex value for each of those. For each neuron, it has a loading in one vector, a loading in the other that generates a complex number like a vector in 2D space. And we order them by the angles. We put them, what that does is that neurons that are that have like positive in the two vectors, they're going to be closer in this ordering. And neurons that have positive negative will be closer, or negative or negative positive, right? So I'm putting together, and that of course makes that when we do this thing, the matrices will be similar in these patches. And indeed, what we get is this. I guess we do see it. It looks a little bit like the connectivity that we built in the bottom from using the cosine. Right? So this is like the cosine connectivity. You put it in. But if we just put two random vectors and we build the connectivity that way, well, it has that flavor. It goes in that direction. It's also similar. The cosine continuity. And indeed, when we run simulations, and this again, let's use simulation, which is fun. When you run simulations in this system, what you have to tune are the parameters, how strong that coupling is, right? So that I played. So we play strongly the variant. No, so that yeah, so because I should have like a parameter in top here. What's this thing? Yeah,
You remind me what nonlinear here? The transit functions that have.
That's a good question.
Where do you work?
Might be. I'm not sure. I've been using it somehow. But it's in the code, yeah, it's really good. I think it doesn't depend on that. So anyway, I was here. So yeah, here you see that these dynamics, and now we're seeing the dynamics of the environment. Only that when I put the neurons ordered in a specific way, I see this. I put the neurons in this sort of space. Looking at it this way, well, when I inject current at different locations, I get the bumps. The bumps drift. So there's this drift, right, that you can observe here. The bumps will be a little different. There's huge heterogeneity, and it's not so good. Sometimes, you know, you see it's very far, the prediction from the this is good, but not always. So these networks are worse than our purely perfectly engineered processes. So they're not as. In fact, if we do, as I showed before, like multiple simulations run over the delay period, what you see is that in fact they are not very good to remember continuity of locations. They converge into just a few pixels. So yeah, so that's interesting. Well, that's suggesting, you know, in ranking networks, very, it's not hard. It's actually very easy to go into this ring attractor regime. It's not a pure ring attractor. It goes into this approximate attractor because it's very slow, the convergence, but it still goes to some fixed points. So then this effect has been known for a while. The ring attractor is a very fragile system. We need to tune it. It needs to be perfectly continuous, translation invariant. There's a number of requirements that are very difficult to fill. So then there's been a lot of research on that. And usually the take on it is there has to be a way of correcting it, because otherwise the system is not remembering the peaks. So there could be mechanisms to correct that. Cellular homeostatic mechanisms is a modeling paper showing that this would work to recover the full spread of the range of memorized stimuli. Slow synapses, these two papers have made the point that if there's like short facilitation, some slow dynamics in the synapses, you can get such that in the timescales of interest, the dynamics is ring attractor-like. Training, so you can start from this imperfect ring attractor and train it to be perfect. And using there are very beautiful work from the Apple lab, very recent, doing that. But at the same time, what if it's actually a feature? What if this would be the mechanism, for instance, to rather was explaining about biases? Because we do have biases, a way to work some locations when we memorize things. So this would be a way in which actually the fact that random networks are more closer to reality. Maybe this is what there's something to explore, and there's this computational paper by Lin here in Shanghai, she's published very beautiful work, trying to make the point that this could be this. And then what I'm going to talk on Tuesday, built on this, is say, well, what if this ring attractor read imperfect is actually very useful to manipulate generic. And I'm going to take this on Tuesday. And just, so one last point about this before finishing is that, all this regression in the recurrent neural networks also to say that, it looks like maybe the way we start looking at all these networks building up from the bottom up, thinking about two populations and the rate, seems like, we could have come to a triangle, figure out elsewhere. But from this recurrent neural networks, just looking at first round, second round, it seems like we were really following some of the basic things that emerge when you just do, random, when you look at the natural dynamics of random networks. There's not a whole lot more. You go to rank 3, you get torus. So there's more, but the triangles and rectangles, maybe that's not something that we should be in thinking. Just to finalize, we have positions in latest situation. Everyone interested.
I think let's go over lunch.
Yeah.
I also encourage the students to go to the first row, okay? So I want to encourage you again. We are in the back and they are in the floor. Let's right.
Oh, okay.
Good afternoon for everybody. And today I give a topic about the Hopfield paradigm and how it is related to the neuroscience and physics, even for AI. I'm from the PV lab in the Xinyu University, and it is in the southern part of China. And PV is with physics, machine, and intelligence. This is I get from when I start to build my lab. But after this year, 7 years, after 7 years, I think about these 3 letters represent 3 keywords in theoretical neuroscience. I never expect this. So P it means the perceptions, and M it means the memories, and I it means the imaginations. So it is a 3 big fields. And if you can invent mathematical law for these three letters, I think you will become a big guy in the field. So, yeah. So now I go to, of course, we talked about Hopfield paradigm. He started from 1982 to establish the whole field. This is the Boltzmann method. He received in 2023, and 1 year later he received Nobel Prize. So in his the memory about his past research, there's a key sentence. It is attractive or maybe so expressive about the Hopfield paradigm. That is, he said, if you can't describe the brain in mathematical terms, you are never going to understand how it operates. What is what is biased in the more abstract level. So I think this is maybe the main meaning of the theoretical neuroscience or the style I much more famous in my own study. So I always bias on the mathematical side, and at the more abstract level and network level and networks of networks level and as a Hopfield emphasize, if you working on this side, of course this side is the physics a lot this side, and then you can pursue some universal laws that is suitable for many subfields. So now you know the Hopfield model is very popular in different branches of the science, including psychology and the biophysics and even machine learning and artificial intelligence. So now we give a little bit history. Maybe everybody knows. In 1949, the Haiping rule. That's all covered by the several previous lecture in this summer school. And 1974, and then a little from the physics department in the Stanford University. They just to say maybe we can describe the persistent states in the brain. And in 1979, and from the Center for System Neuroscience and the Tokyo University, I built a neural theory for association and concept for measures. Then in 1982, formally physics come into the field, and then to formalize everything into physics pictures, and then to tell you that we can use the networks to do the practical computation. I think this is very important things. And then objective lot of physics is enter the field. And then from this paper, it means that and would be begins. And 3 years later, and Hans Blinsky in his career analytically solved this is a Hopfield model, and then to tell the power of the physics in understanding the practical computation in neural network. And then from this year, maybe theoretical neuroscience maybe starts, and so it is very short period. And then after 40 years later, and now people, 80 people also talk Hopfield. It's all you need because you can use them to understand new transform. So it means that now, if you search the Hopfield keyword in archive in all the paper or paper database, you can see the number will be exponentially grows everywhere. So the Hopfield paradigm is very important, right? So last year there is a brain type, and then they just to changing how we think, transforming neuroscience with theory. That is ever computation and theoretical neuroscience. Now it maybe get steps into a more advanced mode of our understanding of the project. So I forget which big I said this word. I just to. But this word is from physics to others because their common feature is they have a physics background, but they learn a little bit to the then finally they contribute a lot and they invent a lot basic rules for these fields. So now we just come back to the year 2024 Nobel Prize, and this I summarize the key contribution. And then the internet and the Hopfield is just to promote our understanding of the neural network. Of course, they cannot solve. They never solve the black box, but it's just to establish physics viewpoint or math or idea. That is more important. This is the physics prize. This is the goal is for understanding. Of course, the chemistry prize is for prediction. You can use AI, and then you can do a lot of the now, if you use the scientific method to understanding the AI, and then you can use this beautiful closed loop. I think this is the 24th century, the big seed in our scientific study. And then the Hopfield definition of the physics, and of course, I think physics is not this, but I think before, no one explicitly say this out. And then the physics, it means that the way you're thinking about the world. Everything. You're thinking about the monkey and thinking about the building and thinking about if you use the physics way, and then you can tell others you are physics, right? Maybe you never learn some physics codes, but if you use the physics way. But in my lecture, I just teach you how to use physics way to think about those complex problems. But I cannot write down mathematically what is physics way, and you can feel like it's just something like that. So now I just talk about in the last 50 years and the physics guide how to promote our understanding starting from 1982 and 1985 the software model, and 1987 and Elizabeth Garner solved the perception model. The perception model also it is a very classical model in artificial intelligence. In 1987, this paper is a landmark paper because you think about the neural network not in the activity space, it is just a coupling space. A coupling space now we call the learning theory. You just search the key network, it is learning theory. I know in Harvard there is a theory of learning group, so it is means that start database to the Ghana. And now in the 1988 and the Sabrinsky and his career and solved this is what we call the non-Hopfield dynamics, because you can write this kind of the dynamics into the potential function. It is not gradient dynamics. This is what my advanced topic in the 2 days later. So I will circulate this class of paper. And then 1990 and Georgia and Sabrinsky solved the perception model that is follow the Ghana's the path rule that they find a forcible transition. So generalization now, it is a key word for. So now we have the very top theory. In 1994, this is orientation tuning. It does a library model. It does introduced by and now 1996, EI balance. This is also we call the physics idea. This the mean field theory, right? And then 2001, it is go to combine the information theory and the statistical physics. And then 2002, it is optimization problem, physics optimization problem. And now come 2015, and we have the generative computing model. This supports powerful model invented by physics. This is based on non-trivial physics. And 2019 from Stanford, there's the double design theory, and this is generalization. What is the underlying method? And now in 2024, and the theory of diffusion model the diffusion model problem by gateway can be analytical understanding by physics. This is happened on the last. So now in this year or next few years, we expect a lot of the insightful paper come in, artificial intelligence and the biological brain and even the theoretical physics. So this is a very golden age for the young student and come enter the field. If you come 10 years later, I see no important thing for you to do. So you can look at this is 10 years, something like this. So now we come back to the Hopfield paradigm. I think it can be summarized in one sentence: all computation is a recall. I think this is borrowed some saying from the old philosophy in Europe. So it means that when you compute something, and then you have the attractors, and then you use the dynamics to flow into attractors, and then you can retrieve memory. And of course, if you think about this, the memory you can use this memory for different kind of the computation. right? So this is a very beautiful mathematical term. If you know, so I know you all familiar with these pictures, and then this is a landscape, right? That this is then the boards that flow on the surface of the landscape. I think in the previous lecture by Cam and you use the Attractor to do decision making and perception and this kind of landscape, very important. And of course, after the Hopfield received the Nobel Prize and Moser, it gives a very intriguing comment. It's the memory at the low point of service that help researcher to visualize how certain thoughts or anxieties can get fixed and retrieved in the brain. And so it means that is we say the development of emotion picture. The different branches of the So now I use a little bit mathematics to tell you one slide to tell you how the Hopfield think about this or the way they're thinking from the beginning. Here I think the way it means that I just come down here because Hopfield think about how to invent, how to expand the memory. So I think it is physics way. What is the physics way? So it means that he first had this kind of picture first, right? Then they do the reverse engineering down to what model or circuit can realize this kind of surface. So this is the inverse way. It is not from the, maybe we can call it this top down. It is not the bottom up. It is do not be constrained by the molecular detail or experimental detail. If you look at the 1982, we know more experimental data because the technique is so low and you could not measure a large scale of the recording of the level. You have AI not there, and you can only do this physics way. You can, for physics, you can think about this energy landscape. It is very popular concept or very standard concept if you learn the physics course. So this then you invent this is the energy landscape, and then you can construct which model can realize the memory, right? If you want to realize memory, you should have what is memory, how to define memory. Then you use define memory as a pattern. As a pattern, it is a high-dimensional vector, right? You put how many vectors do you want to retrieve? This is a very natural way. And then you use the brain to retrieve memory. You do not use the computer to retrieve memory, right? You brain retrieve memory, then you have a dynamic state, right? The brain is dynamics, and then you have another brain state. Then you use a high-dimensional vector to represent the brain state. So now the last step means that how do you check whether a memory is retrieved or not? Right? If you have two vectors, one vector is fixed and the other vector is dynamics, and then you just calculate the dot product, right? It is a confine similarity because if these two vectors it is exactly the same and the parallel with each other, and then of course the memory is retrieved. Otherwise, they have partially retrieved. So then you have a dot and the product, then it is a scalar variable, right? The scalar variable, we want to maximize that. Then you should put a nonlinear function. But of course, if you look at their papers, maybe this is a quadratic function, because quadratic function can make always these functions positive. Then we can locate put a minus, and then you can search for the lower point. Then you can recover the energy landscape. While the ball or the state will flow to the low point, and then it can be met. This time the maximize, you put a minus, and then it goes to the lowest point. Then the remaining task to determine which function you choose for f, right? So of course for physics, the first simple thing you choose is a quadratic function, and then quadratic function it means that, and then quadratic function is I should write something very simple thing. So it's a quadratic function. And then you have the Xinyu, this S, this is equal sum over mu plus or minus, and then you can sum this, and then you can sum I Xi mu Xi square and sum over mu and expand, and this I Xi mu Si. This is very basic, but maybe in the high school you can do this. So So sum over j equals j mu xj, then rearrange this term because in the sum you can rearrange. It is sum over ij, sum over mu cos I mu cos j mu xi xj, and then you put our bracket here, and you just to introduce a definition of this is the count of jij because the mu is sum out and you sum out mu cos I mu cos j mu, and then you can come back to this type ij si sj, and then from physics to do it, you can do it less than 1 minute. If you do it in 1982, and then you can get Nobel Prize. So you don't imagine Nobel Prize. It's very hard to right? So now in physics, I think this is a high dimensional vector. And for physics, you can go to some spin. Just always use the different kind of the symbol. But the same, mathematical same. There's a spin. Of course, this can be continued or something like that. It can be brain can find can continue. But of course, we can make a more abstract simplification. We can make a binary state. Maybe just take the plus or minus one. That is a spy or silence, and then you can come to what we call this is a Hamiltonian, right? This is come to the physics, right? Maybe this is one the starting point we want to understand memory, and this is brain. We just this is simple logic and then come to physics as a Hamiltonian. So then that is what the Hopfield said that it's a mathematical term to understanding memory. Maybe it is not true, but this is very beautiful setting. And then you have this but for physics, because this is some of mu, you can store a large number of the pattern, and then you just be rescaled, and otherwise this term is very big. Very big. So the coupling in the brain could not be infinite in mathematics. So you sort of rescale to order one. So you put this, and then you can get this Hamiltonian, right? If you get the Hamiltonian, how to realize the dynamic flow on surface of the energy landscape? This way is already formulated by physics, because this actually in our field is Monte Carlo. Maybe you are guy heard about Monte Carlo, right? Monte Carlo aggregate it is very popular in the computer science. You can do the sampling this point. So Monte Carlo means you just roll down the energy. How do you roll down the energy, right? You just each time you pick up a spin, right? You just switch this spin. If it is already start one, and then you want minus one, and to check whether energy increase or decrease. And then if you want plus one to minus one to decrease, then go. If they increase, do not go. And this is the in this way it can help you to maybe fastly convert to the point. It has no fluctuation. And this we call the zero temperature. Because even in the computation you have no statistical noise, right? And if you do this way, it's actually how to update. This is we are called how to update the state or the neural state. So we can get the sign function. Because this part is a you can see it's a local field, right? It is a local field. That is all the neuron. It is still all its neighbor, neuron, right? I just to draw. If you look at this neuron up or down, how, right? You just look at its neighbor. You just compute his neighbor. His neighbor is J, some Ij, sigma J, maybe the previous J. And then if this is we call the field, right? That is in physics, this is P. There will be a magnetic field. It's something like that, right? So if this field is positive, of course it's be up, right? Then it parallel with this field, because you make it a very cold apply a very strong magnetic field on this spin. This spin should be parallel with the magnetic field. It cannot be reversed. Otherwise, they will overcome a very huge energy barrier, right? So this is you make this thing. So the base knowledge from physics to it is the same. That is you receive a strong current, right? Strong current, and if the current is positive, I think will activate this neuron, and then you go to start, right? So this is a similar similarity between the physics and the real brain dynamics. So then you have the phi function here. But now if you look at the classical textbook, and then this is what we call some dynamical equation. Right, dynamical equation. This is psi function. You can look at if you let the time as a spatial index. This is actually the perception model from the t equal to 0 to t equal to 1, and then come back and t equal to 0, t equal to 1. This is actually the perception. So I think I remember the Hans Bringy said that people in the brain science may be correct. The feeble network is not more biological than the recurrent network. The Ham does disagree about this because this is the same thing. You could not say the recurrent is biological, feeble it is not biological. It is dependent on what you can interpret. Right? I can interpret this as feeble, but of course this is a recurrent network. It makes no the base difference. So now we can use this event dynamics equation, and we can. If you run this equation and the energy will be going down, and then you give the fixed point, and then you retrieve the memory, right? So this is completely complete whole story about this. In never mind, you can realize so this is what we call the.
So now is a positive function, which is positive function of the sphere, right? What's the information?
In this way, it means that beta is order, right? It's a constant singularity. So it means that this can be positive, can be negative, it can be parallel or anti-parallel, right? So in physics, I want to be maximize this term. It cannot be positive or negative. It will affect my optimization process. So we put a square to make it not arbitrary, right? No can cause some confusion. So this is the map of square, and then square, and they're always positive, and dump all the memory and to the minus. Then we can turn the maximization to minimization, because physics favor minimization, because they always talk about the ground state and something like ground state is on ground, kind of on the sky, right? So we put the square. Of course, you can put the power 4 or power 6 and power 8. And later I will talk about this. And transform it is put a different power here. So, of course, you can put absolute value. It is okay. I think it never mind. You never mind. You can do it, right? So if you can do optimization, it doesn't affect your optimization. You can do arbitrary. Right? Yeah.
So we like identify or optimize this actually in the Hopfield asset we will get the field offset the next day, right? And then
Yeah. So now we talk about the other choice, right? Because in traditional Hopfield model, and then you sometimes say what your memory that down in the between, and this we call the superior state. You could know that use that back to your memory retrieve, but then function. For example, you go to the qubit, right? If you go to a qubit, put a qubit, then you can eventually, if you expand, you can use the 3-body connection. Actually, it's how many body connect in your model. Maybe pairwise is not enough, and then you use the 3-body, because you know if you introduce 3-body interaction, and then energy landscape will be reshaped. And then if you reshape it happens that your stored memory can be restored, and then you can cure down, you can cure you can avoid some drawback in the traditional Hopfield model. This is what we call in the 10 years ago, and the Hopfield protocol, the dense associative memory. You just have the power to arbitrary power n. It is 1, 2, 3, 4 up to 10. Then you can include as many order of interaction into your model, and then your model will become powerful to interpret the data. And even the transformer, they argue that this f function, it is an exponential function. Right? This is exponent. You can treat it as exponential function. You can treat this function is an exponential Xinyu dot x. You can treat it. Of course, this is also positive, right? Also positive, and then you can. But if you use the exponential, and then the storage capacity of the Hopfield model will become exponential, right? This is why the transformer becomes powerful. This is interpretations.
Do you think there's any mechanism that will a biological neural network may implement as Hopfield?
Yeah, but now people struggle to integrate, to map it the transformer into the real biological, but not exactly the same. But you can map, do some similar mapping. This field now is still being growing up. Growing up. This is what I emphasize. It means that the AI now it can be constrain our hypothesis to study the brain, but you can narrow down or just to restudy this bridge between the neuron and AI. It is all, but this is still going up. People never know the exact final answers. So now I think we can emphasize from the birth of Hopfield to the birth of the deep learning. It took 24 years for the birth of deep learning. So this is why people argue that from the last year's Nobel Prize, because people Hopfield did use this, Boltzmann machine use this, Boltzmann machine use this. What's powerful now is transformer. It is not related to Hopfield. But you take 24 years, maybe so long, people forget the original idea. So now we should come back to think about the physics origin or the concept origin, and then we can cure the problem of the transformer. So this is what I call in my title, learning efficiency and liberation. Learning efficiency is for training corpus, and the representation geometry is for understanding. So this is two key issues in my account. I just talked about the transformer. We can see recently there's I think the paper come from MIT and now neuron. And it's the key value memory. That is Professor Zhao asked the question. And then you mean that you look at every day. If you try to the library to find a book, if you do not have enough time to read the whole books, and then you search the keyword, right? You just come to the backside to check the index, and then you look at on which pages, and then you check the specific content. I think this process is very similar to the transformer. Why? Because you have a query, right? Which word you want to be to check, and then you just to match with the key, right? With the key maybe this matching process happened. Argue maybe not really true. Argue in the hippocampus, and then you just to do this matching and calculate the score, and then we call the max probability. And then you use this score as a weight sum with the memory content. This is the value in the neocortex, and then you update your representation, update your query, and then you update many times, and then it converts, and then you can retrieve what you need. So this process and the basic question is very similar in a similar form, not exact form, in a similar form with the transformer structures. So this is what we call the key value memory.
Only difference between this one and the traditional Hopfield model is just replacing the echelon with this exponential.
Yeah, you just reframe this is quadratically to exponential, and then you can get this. You mean this one? No. Yeah, this slide means that you can use a Hopfield paradigm to capture the form of the transformer. Yeah, you can use this. Now I think in theoretical field, people use this side to understanding what transformer do. This is
very recent book. They're showing that the memory happens, right? The transformer is not in like this layer, probably in this MLP layer. So the word of memory is stored in the transformer neural network. It's not entirely hidden.
Yeah, right. Because this is a transformer blocks. Because we have NLP. NLP maybe have to build a very nice geometry, representative geometry to do different kinds of the computation.
So there are many different interpretations of it. This is just one of them.
One opinion. It is not converged now. It is a lot of interpretation.
Traditionally, I will understand it by adding a Boltzmann distribution needed to be just applied it into the E, right?
Yeah.
So I have the Boltzmann.
Yeah. The formation something it is something like Boltzmann distribution.
doing that is like doing normalizations to know what current thing is based on all the knowledge I have. What do you think, like, how, but do you think it's necessary to introduce probability here? Overall?
Here it is
Involved in the Hopfield analysis.
in Hopfield, but because the force has energy, and the energy means that on the energy surface at a different point, and then you just give a different point, just at each point at the sample. So it is natural to invent some probability distribution of that state. We call the memory state, like this.
Like minimizing the additive is equivalent to maximize the probability.
Yeah. But even in our current stage of AI, people also believe when you're doing the computation, there's you just each time you retrieve a useful concept state, and then you do different kind of that is a compression maybe has a very hypothesis. That it means that all the large language model is a complex different information into a concept representation, and then you just to act very abstract. You never know that, and then you based on that abstraction. Of course, it is a probability distribution. It's not single concept. So you can do various kind of computation. This is a hypothesis. No mathematical proof. Even people now in biological science struggle to do some the manifold viewpoint for the neural computation. I think it's the same path to the same scientific goal. So now I just to bring people back to the very earlier time from the Hopfield 1982 to Miyasa, and this is today's earlier morning that this is a talk about the Miyasa paper in 1988. The event you saw the monkey has had a sequence of the stimulus and the different kind of picture, but the picture just has no correlation. But you saw there is sequence to the plants, to the monkeys, experiment, and then you check in the monkeys the temporal cortex and record the cortical activity, and then you measure the correlation between the neural activity. They found the correlation decay with the stimulus index up to 5. This is what we call, I think that now in the field we call the magic 5, because in Brunei in 2008, the Danny Amit, because Danny Amit, they proposed this kind of theory to interpret the monkey experiment, and then this is called magic 5, because in the Danny Amit's the theoretical paper, they saw exactly the 5. So this method is very exciting, because they can use the toy model to capture the key file to the monkey's experiment. Maybe this is a few triangle of the theory, and this is up to 1993. But in 2019, and the Fukai from the Japan OIST, and then they revised this theory. They claim that this is C, it is a habit, the habit strength. Because in Hopfield we have the habit, right? We can see that this is a habit. JJ is a habit, right? Maybe here is a habit. But if you put a C here, the habit you can tune the habit strength, right? You can put the C here. You just only put the C here, and then the C, if positive, it is the formal habit. But if the negative, we call it anti-habit, right? Anti-habit. So the Fukai learned that if you use the anti-habit, you can largely expand the file. You can largely expand to 2 times or 4 times and 6 times the file. So they claim anti-habit may be very important. So now in 2019 and in the community, what is the role of anti-habit? This is the distance. This is for example, you saw this picture, and so this is 2. This is 2. So the 5 is means you saw up to the 5 picture to the monkey, and then you check the correlation activity. Maybe later. I have a medical term. I just describe this is the history of the experimental and the theory in interplay between each other in the maybe the 30 years or 40 years. Now we come back to some biological detail. Before we say this is 2 next paper by Miyasa, and they say that the monkey's temporal cortex, observed to be able to convert the temporal correlation of stimulus into the spatial correlation in the neural activity. I think this is how it's very intriguingly for physics, because physics, the space and time is two important concepts. When Einstein invented the general relativity, this is all about the space and time. And the time it is a temporal correlation maybe of the stimulus, and how the monkey's brain transform this is temporal information to spatial information. Right? Spatial information, it means that the overlap between two attractors or representation in your brain, the high dimensional representation, geometry in your brain. So now we come back to the idea. To idea, it means that what we call now, you can build a coordinate model is meant that you have ID memory item, the identically independently distributed, just a different kind of picture. They have no correlation one by one, right? This is new, it is your pictures index, right? So you just introduce an arbitrary correlation scale, right? This is the D, right? Where you can call this a temporal the window, temporal window. For example, if you choose one and then it is one. It is a neighboring stimulus. You have convert the neighboring stimulus into the spatial overlap, right? This is what also in the monkeys, whether in monkeys' brain or in our Hoyer models activity space. Then we found the attractor is not separate. It is partially overlaps. But in the traditional Hopfield, each attractor it is a fixed point. And for example, the one pattern here, one pattern here, one pattern here, and this is the side of the circle is the Beijing size. And then if you start here, then you convert to memory 1, and start here will convert to memory 2. But now, if you introduce this is a temporal correlation in the stimulus, for example, you transport the stimulus to affect the synapse structure, and then in your brain, you will control this overlap guy, right? The overlap guy, what it means is overlap guy. It means that if I turn back to here, this is overlap guy, right? This is the pattern index, for example, 6, 7, 8, 11, it is a central, right? And then on the both sides, you can correlate from the 12, 13, 14, and this side is the 10, 9, 8, 7, and the window size, it is 5. It is 5 here. It is 5 here. It's something like this is what we call the distance. The distance means that depend on your sequence length in your stimulus provide to the monkey. So we now look at a little bit detail. It means that now in the GGA, this is in the 1993 in the Amix model, explain the Miata, explain beta, use D equal to 1, right? It's just to use this is a memory and this is neighboring memory. Try to use the memory and the neighboring memory to construct the coupling. Later I will show the mathematical detail to how to write this DIJ. This is D equal to 1. Right? D equal to 1 in the intuitively understanding, you could not have the distance up to 5 because naively maybe it is 1 or 2. You cannot have the 5 at the long range correlations. So actually D equal to 1, they can give you the perfect the matched experimental finding. D equal to 0, it is no the neighboring pattern. It is cannot affect the coupling, right? You can see, this kind of coupling, the mu is at the same index, it cannot be at the neighboring one. So this D equal to 1 is Hopfield. If D equal to 0, D equal to 0, and then this is a fixed, this is attractor separate with each other very far away. It's separate. But if you join this attractor together, have a certain overlap, you just increase D equal to 1, and then you can do this is attractor overlap. What's the benefit for this attractor the overlap? It means that if you have the memory, you can continue to shift from this memory to this memory and to this memory. If the memory is separate far away, you cannot easy to go this memory to the other memory. So that is how we can match the monkey's experiment, because the monkey, of course, the memory can be smoothly carried from one to the other. So of course, then what's the motivation we introduce arbitrary D? It means that this is, I think this is based on the picture about the SGDP and the event by Professor Pu in the ION. It is had a certain of course it is asymmetric. actually at a certain level, the depression and the strength has a certain temporal window. So it means that if you give a stimulus to the monkey and the stimulus will cause the neural activity, and this neural activity help to construct the coupling, but this is where we incorporate some time scale or time window. It does not happen on the one model or the same model. So we can consider some delay effects. So this is the D, maybe it will be correspond to this kind of the experimental finding.
Spatial is the physical space in the brain.
Yeah,
space in the memory space.
Yeah, for example, you can give a stimulus and you can measure the neural activity. And then the second stimulus come in, you can measure the neural activity, you check the neural activity, and then you can see this is two factors. So the visual pattern is ordered. It's not separate.
Someone said he goes to infinity because this means that you have some
equal to infinity, but later I will solve simulation result. If it is finite, then it will give you the surprising results.
It's not clear. Sorry. Is it means that the memory patterns are correlated, or is something else?
No, the stimulus is not correlated, but your brain representation is correlated. Yeah. That is transform the temporal information into the correlated spatial representation in your brain, the representation.
What is the memory? Why you never had a single network or
You mean this term? This is memory item. You can see this is the one picture, this other picture, and this is third picture. Some pictures and signals, or the memory you want the network to remember. Later I will show some theories about this. Right now I write it into mathematical term. Right now, how to construct the JIJ? Now you can see the first term is the habit, right? In the habit, I just put a C here. That try to integrate, try to incorporate the Foucault's table because Foucault's they introduce C here. But now I add another term. Another term is another sum. This sum we call this is the temporal the time window, maybe the time window length. And then you can see now you can see I mu plus R, and they have some kind of a delay, right? This R, the delay can be 1, 2, 3, 4, 5, 6, right? But the mixed table they're doing only E equal to 1. But the Foucault's table they only T1 the C. But now in our case we try to put a gamma here and put a enlarged B here. This is our contribution to this Valedictorian model. No, it's just some analogy, maybe not exactly mathematical exactly corresponds. I just some kind of the motivation. Yeah. So now we have a cycle sequence. Now this is you can interpret the pattern in the original Hopfield. Now it can be solved in the cycle sequence. That is a period. It is similar to the experimental setup. It just use a free picture. For example, if the pattern is maybe it is 4, it means the equal to 4 here, and then now this pattern is stored in a sequence. This is 4, this is this is 2, and this is 3, and this is 4, and then it is a factories, and then you can come up here, and then that's the 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. You can solve to the similar to the experimental the monkey experiment data. Then when you solve this, it doesn't matter the monkey strength. Right? You measure each stimulus, you measure the activity. So now we can have 2 terms. In our case, now we have the non-delay habit. That is the habit on the same model. So this the strength is the C, but the delay habit we call the gamma. They have this is we have to compare with each other. So the gamma is very important, very important role. We can observe new predictions when it's writing effects. Now, based on this is a Haiping construction, right? It's a delay or non-delay, and then you can find a very interesting mathematical idea, mathematical property. It's pretty easy, right? For example, if you put the gamma is equal to minus gamma, right? If you put this gamma, gamma can be negative, right? We know from chi the C can be negative. It's anti-Haiping, but this we can call anti-delay Haiping, right? Because the gamma can be negative. If you the gamma is negative, you can tune. You can do the second operation to cancel. This is minus gamma, right? For example, I just write very easy. I don't know whether easy or not. For example, if d equal to 1, and then the second term you have c I 1, c j 2, right? And then plus c I 2, c j 3, and then plus and c I 3, c j 4. That is 1, 2, 3, 3, 4. Because each step this is a mu plus 1, right? This is mu equal to 1 plus 1, 2, 2 1, 3, 3 plus 1, 4, and then also, right? And then originally you have a gamma here. Now we put a gamma equal to minus gamma, and then then this is what has a minus here. And then how to cancel this minus? And then you just put the c2 to c to minus cn. The n it should be odd value or even value, right? Because if you put the 1 minus, you cancel the other minus, right? If you put the 1, then the 3 is b minus, and the 3 is b minus, right? And then that is essential. So you can cancel the gamma, right? The minus. Also, you can put the even number. For example, 2. You put the 2 equal to minus. Then it means that this minus the original minus, and then you put the 2 equal to minus, then you put the minus here, and minus, and then positive. Then you keep the coupling, it remains a coupling in balance chain, right? So it means that you odd number of pattern and the even index or the odd index, and then you can keep the everything balance chain, the coupling balance chains. So it means that even you tune the anti-Haiping, and then you just to tune the memory index, and then you can keep everything index balance changes. So this means that this is a mathematical effect, and later we can see how the brain or how the neural network can do this kind of optimization automatically, right? But before doing that, we just to find our construction has this kind of the very simple mathematical property. Now the problem, if I want to increase the d equal to 1. Now if I increase the d equal to 2, this will become very complex, right? Equal to 2, it means that 1, 2, 1, 3, right? And 2, 3, 2, 4, right? So because if the d equal to 2, and then you can make plus 1 and plus 2, right? So if you plus 1, for example, you look at these two terms, you cannot make the even index or the odd index to minus. You put the even index to minus, right? And then this is 3, it is even this is a odd index, this be minus, and then this term could not be minus, it's positive. So you could not cancel out this is a minus term. So it means that for d larger than 1, this mathematical symmetry completely lost, right? So before doing simulation, we know this. Now we can go check whether this is true in our network simulation. So this is the key point. We found some in physics or in mathematics this kind of symmetry breaking because you could not do some reverse to keep the ZZ is the same ZZ. So this is a much intriguing, very intriguing the network effects for the memory. Yeah. Okay.
But maybe there were a question. You had a question?
Okay.
want to I just want to make sure that you're saying when D is larger than 1, then you want to investigate or validate whether memory has a complementation model or what you
Yeah, but I'll back the memory landscape. Later I will show some evidence. The memory landscape will become very complex. Later I will explain that.
If you let's take a 10-minute break.
Showing some pictures now. And extending the spectrum. So, then you will not be able to is a 5, the classical result, and the D equal to 2 at equal to 2, and it goes to the 15 or something, and then you can tune the level of the spatial correlations. But if you look at the memory landscape, they also discussed, right? If the D equal to 1, and then we know there's a even index or the odd index will be the memory will be changed, right? If you look at the D equal to 1 and gamma is minus, and then you can go the odd number or the even number will be a lower point here, right? The overlap will come to the negative overlap, the positive overlap never appear, right? If you gamma go to the positive again, and then this memory will be going up, will be shift to the positive memory. So it means that there will be scatter. But if the D equal to 3, because rather than 1, and if you tune gamma equal to -1, and then it will be appear very irregular lower point. And how to find this lower point? I think not mathematical proof, but you can do some simulation that is optimize this kind of the Hamiltonian, and then you can find out which memory will be retrieved and which memory cannot be retrieved. So it means that if you tune the value of the D, you can control which memory cannot be retrieved or can be retrieved. That is to start the memory landscape, and then this is go beyond the traditional Hopfield model. So this is now we can conclude that D can trigger some fluctuation in the optimization of the memory. This is our memory. We can see some detailed picture. For example, you look at this. You can look at this is some kind of something like oscillation, right? It is positive, negative, and this is we call the oscillation retrieve because we know in the traditional Hopfield has a negative pattern, right? And now at this point we have the negative overlap, but it has a positive overlap here. But if you D rather than 1, and then the positive one disappear and negative one appear, right? So each point here it is can be correspond to the minimum of the energy function of the landscape. So this is oscillator retrieve, and this is a single retrieve because only one pattern can be retrieved. This is a traditional Hopfield model, and this is a correlated retrieve because it has a spatial correlation between neighboring patterns. For example, you can see this is the center is 5, and up to 8, and 5, 6, 7, 8, maybe 9. This is 5. It is a magical 5, and so you can use. I do not talk about the detail. You can observe this kind of the phase transition. You can, for example, from the single retrieve here, this alpha and the gamma. Alpha it is a memory load, that how many pattern you need the circuit to memorize, and the gamma is it is not delay Haiping strength. You tune the delay Haiping strength, then you can go to the single retrieve phase, and you can go to the oscillation retrieve and the memory retrieve. Oscillation retrieve only appear on the negative gamma in the this side, but in the positive gamma you have the two phase in the single retrieve and the correlation retrieve. So now now we come back to what is the this part is the oscillation retrieve. You put a gamma is negative. If you go back to the paper by the Frank Crick in the 1983, this correspond to the G3, and in the same year, in the same period, and Hopfield published the side-by-side paper. It's called unlearning because it put the minus, that is to cut down some part from the heavy construction. So this is called unlearning. So the unlearning has a stable effect in critical memory. So it means that so we suspect that this part is correspond to the unlearning effect. Maybe because the memory can be retrieved and can be removed. This is similar to what happened during the sleep period because the coupling will be readjusted and to keep some important memory and remove some unimportant memory. So because of the time limit and then this part maybe I will be briefly introduced. Then we can study some time order of event, for example, episode memory, and then you just break the symmetry, the symmetry of the JJ, because in previous, if you exchange the neuron I and J, the JJ is the same, right? For example, in the traditional Haiping, you just exchange I and J. This is a Haiping, it is a symmetry. But now we can remove the because this has a two term in the originally. We just remove one term, and then you can make the JJ become a symmetry, because although the first term is Haiping is symmetry, but the second term this is come from the delay Haiping interaction. We can make that their symmetry, and then make that a symmetry. We move our dynamics to, because if our symmetry we do not have the landscape, then we move to the recurrent neural network. Right? That this kind of I think everyone familiar with this. If you remove this, and then you can write that as a matrix multiplication, because the Kersi transpose X and Kersi, and then this mathematically very surprising means that then this X matrix corresponds to a circular matrix in the signal processing, maybe in computer science and electric information engineering, and then they play this kind of matrix very frequently. But now I just find in the memory system we have the same circular matrix, but this kind of matrix has an analytically eigenvalue, analytically eigenvector. So it means that it gives us opportunity to analytically understand this kind of a system. This is a circular matrix, and you can see if E equal to 2, you in each row there has only 2 gamma, right? And the C, of course, D is on the diagonal term. This corresponds to the heavy, right? This E equal to 2, the P equal to 5, and then this X matrix is 5 times 5. If the 100 times 100. So if we do this, then we can see much more dynamics of effects, right? Then you can see if you tune the D, right? The D, the key parameter, you tune the D and overlap, it just calculated by this. This is the memory you store in the system. And then this is the activity you observe at the moment of T. And then you do this kind of overlap, and this is the time, and this overlap you can find. You can find as a sequence retrieve the memory, right? You can the maximum overlap and then decay, and then the overlap shift to the neighboring pattern, and then to neighboring pattern, and then you can observe the peer. This is oscillation of the cycle, and then you can, this is one cycle, second cycle, third cycle. If you tune the number of the D, and then the frequency of the retrieve will be changed. And it means that the time window for the snap integration will affect the memory retrieve the frequency in the network effect. So it means that we can go to the microscopic detail of the coupling to the network effect to retrieve the sequence memory. It means that you can encode some episode memory into the system, and then let the episode memory to be repeated again and again. And then you can study different kinds of how they affect the sequence retrieve. I skip here because this has a beautiful mathematical result. You can determine the random metric theory to see the eigenvalue of the coupling of this kind of symmetric uncoupling, and they have the very analytical result. Maybe this is maybe need for the mathematics to maybe prove if one day. not go to here. And you can study the local stability of Zhao copy, and then you can see when they lose the stability and they go to this is retrieve the episode memory, and this is the decay to the yellow point, and it depends on the stability of the brain state. And also you can take the diagonal exponent, and you can find if you increase the memory load, you will go to chaos. But in the between, you have a correlated retrieve phase here. So now because the time is limited, and then I go to the other part. It means that now we can invent some more decomposition learning for the deep level. That is what I study Hopfield model. You can inspire the new algorithm for deep learning. So this is what I emphasize. How to invent them for example, the layer structure. This is not recurrent structure, right? The layer structure. Then for each connection, you use the you use the Hopfield rule to decompose each W, right? Because as you know, here we have this Hopfield coupling. It has a 3 matrix multiplication. But you think about in the perception model, each connection can be constructed this way, right? This is in a strong contrast to the current training by backpropagation, right? Backpropagation, you just train a single W. But here, we decompose the W into three terms. It is that the first term, we call it input pattern. So when you train a perception, there's a pattern, right? The person may be doing some memory, right? So it is a single pattern, and then this sigma is some diagram. It is a video score about how important of this pattern. And then the C2, it is an output pattern. So you decompose this, and then you just to put into the perception model, and then you can decompose. There has the previous level. There's activity, and then the weight is by the Kersey head. Kersey head, it is some input pattern, right? Weighted by input pattern, and then some OI from the previous layer, and then you get the kappa alpha, right? Kappa alpha, and then you just let the sigma and Kersey the output pattern weighted by the score and give a weight, and you give us that weight, and then you sum over alpha, and then you part of some nonlinear function, and then go to the next level. So when we interpret this, we just focus one single neuron, right? So here we tell you one single neuron is actually a perception. Right? So the single neuron is not a single neuron, it's just a perception. So you can find some very intuitive case. This is maybe it is a dendritic computation in our brain. Right? So dendritic computation, you just a linear processing of the input, and then use a nonlinear dendritic function, and then you output. So in our case, if you understand in the Hopfield parity, then you can understand the dendritic computation. So dendritic computation, it means of actual model of maybe a biological model of the Hopfield computation. So this is what we say. It is has a very intuitive connection to 2030 the pyramidal model neuron as a 2-level neural network. So this is very strange. After 20 years, we invent some mathematics, and we find out some biological paper also talking about this kind of the similar things. So this is just show that training the sigma. Yeah, now we training the sigma, the C, the sigma, the technical sigma and the C. We train these three. We do not train one single W. We train these three. This is a latent pattern. We call it latent pattern, not the stimulus, the external sensory input, because this transport the sensory input to the latent pattern. We try to find the latent pattern, then use this latent pattern to construct the coupling. Rather than you use the backpropagation to train coupling. If you train coupling, you never know something. You never know something, right? Even you cannot build the connection between the dendritic computation and the single point neuron. Right? So we can just reinterpret this result. So we can call the number of the mole. The mole is the pattern. The number of the mole the layer perception learned is equal to the number of the dendritic branch. The dendritic branch is the biological term. The number of the mole is from the algorithm, from your setting. So we can make these kind of the connections. So this is a dendritic branch was a point new. Now I talk about how to train this system. This is very efficient way. Why? Because you have the input pattern here, all right? In the output pattern here, the dimension of the input pattern is n. The dimension of the output pattern is n, right? So if you want to search which pattern the neural net will learn, and then it is m plus n, the number of the parameter, right? So then, how many patterns, right? That is how many patterns stored in the system. It is small p pattern, and then the training cost is small p times m plus n, right? So this is what our new training strategy. But in the traditional backpropagation, it is the W. How many elements in W? It is m times n, because it's a matrix m times n. So this is a quadratical computation complexity. This is a linear complex complexity. So you just use some kind of density computation, and you can reduce one order of magnitude in your training cost. So your training algorithm will be one magnitude order faster than the traditional backpropagation. So this is what we call the learning efficiency. You're just doing this kind of the Hopfield decomposition, right? But in the Hopfield, this pattern is this pattern is the same. But in our case, this pattern is not this pattern because it's an upstream pattern and a downstream pattern because you want you to understand the layer propagation of the information. So we have this, but this is if you compare to SVD, so this is maybe it is a bit different because the pattern not necessary to be orthogonal, and you can control the number of the node, you can control the number of the dendritic branch during the computation, and you can the score can be negative, it can be very negative to that kind of the pattern. So we can use this kind of the backpropagation in the mode space. This is not the coupling space. It's much more faster, and you can integrate their computation by geometry, right? This is we test on the it's quite good and comparable to the BP, the backpropagation. But we can use the P, the number of the mode, plus the 20 or something. This is because it's centralized. The computation accuracy. So you just use a very few number of the modes to compute. If we can study the geometry, you can look at the geometry. You can use the two kinds of stimulus. For example, you use the stimulus to 0 and stimulus to 1, and then you use their PC components to K component construct of Q matrix, and then you're doing this single value event by mathematics. They can calculate two subspace, the correlation of two subspace. So you can do in this as a computation. You can see our mode decomposing learning. It can be rapidly to make the two subspace orthogonal with each other, right? But if you use the traditional BP, they just maintain a very high they will entangle with the two subspace. So it means that this is a very nice priority for representation geometries, even on training data, even on test data, and also can give you very nice orthogonalization of the subspace. If two subspaces is orthogonal with each other, you can cleanly to separate the manifold, and then you can get the very high accuracy of the representation. Even the last part I just emphasized, even you can use the similar paradigm to spiking neural network, and then you can make the connection to the data analysis in a real experiment. So I think in the traditional spiking neural network training, it's very expensive and very hard to train, and we interpretability. But the merit is brain-like computation, right? Because now you have the voltage and the snap filter, and you can incorporate and many biological detail as in your model. But here we just generalize Hopfield to spiking neural network, and how to generalize I should use one slide to say low range hypothesis that is by the Zhao, by the Professor Zhao, and that means that you can decompose the data at here. I think the Oscar paper, I think he never remind us. The Oscar paper, of course, it takes back to the Hopfield network in 1982. You use the two kinds of pattern here, right? And then you decompose into this is the basics and the basics vertical to the input coupling, and then you can use their coefficients to load down the dimension of the original activity. So this dimension, it is R, is much larger, much smaller than N. But in our case, we generalize this data to have the score function here, and the M and N, it doesn't need to orthogonize with each other, and then it is generalized of the Hopfield model, and you can use the circular metric or maybe not circular metric, some fine-tuned metric to write the data and metric multiplication. So the key idea is here, including the low range or not low range. You just remember this one. So this one can be used to layer perception, can be used so traditional Hopfield can be used to explain the monkey data, and can be used to this stacking network. So it is very good hypothesis or very good principle to understanding the neural computation to invent new algorithm. So this is a low range, and we can include. But now we use this type to recurrent connection. We just use the incoming pattern and outgoing pattern, and this is an important score that we call the mode weighted matrix. It is a diagonal. So of course, if you use this paradigm to train the spiking neural network, you can reduce the computational complexity from n squared to linear n. Right? So you can use a linear algorithm to train a very complex spiking neural network. So it means that linear is very fast, right? You cannot complain about linear is slow, right? Because we have a very powerful linear algorithm. So now we can use a memory potential and use a discretized memory potential, and this interpret the memory time scale, and this is the input current, and then this is a refractory factor, because if you spike, and then this will go to 0, and then the condition will be reset to the bottom line, and then this is a and because this is cannot be well defined, but if we can use surrogates proposed by Frank, taking the back proportion. And then this synaptic current, we can induce a single exponential decay, and also we can use a double exponential snap filter, and you can include as many possible biological detail into this model. And then please remember the W is trained in the mode space, and then we can see where we can test in the context back computation. And this I think you already introduced in the previous lecture, and this is maybe like the monkey or the neural network to obtain selectivity to one feature of the noisy sensory input. So we test this has two contexts. One is the motion, the other is a color, right? So it means that we can use this type of training to project to use the input pattern to project onto the low dimensional attractor. So it means that now we find the four attractor in the representation space, and it corresponds to the left attractor right, and this is called the motion, and this is called the color. And then what we want to test it means that this is a study model. If we switch the context, we want to see how the neural activity flow in the representation space. So it means that originally we choose the left attractor, we give the context for the left attractor, and then all the neural activity or trajectory will flow to the right one, and then we can do a very high accuracy of the decision making. And then at that point, we switch the context to from the red to green, from the motion to the color, and then the neural activity just leave the attractor of the red attractor, and then they go directly to the green one. And then it means that if you switch the context, you can observe how the neural activity going from one attractor to the other attractor, and you can see the detailed trajectory for this low dimensional mapping. And this mapping, the key component, it is our input pattern. You just to provide a very nice space for you to doing this projection. And also you can project to the kappa and the long range hypothesis, and then you can observe the similar things happen in this low-dimensional representation. And finally, just to give you a few take-home messages. One is the Hopfield model. It tells us its memory is an optimization in mathematics. And also the patterns exist in sequence learning in deep network because the pattern, it can be rendered as in Hopfield, but it cannot be rendered, it can be structured in the practical training. And also low-dimensional attractor, it can be observed in the spike neural network, right? And it helps you to understanding how decision-making is going on in the low dimension. But the point is you should find that kind of the pattern, the latent pattern in the spike network. So the last point is efficient learning possible within the Hopfield paradigm. You can invent linear complexity for training people perception and also for training a recurrent spike neural network. Okay, thank you.
Really thanks you for the very nice introduction, and thanks the organizing committee for inviting me here, because I'm basically an experimentalist, neuroscientist, of course. So it will be a little bit weird for me to talk in the CNeuro computational neuroscience summer school. But I think what role I can play here is to like really bridge this experimental field and the computational theoretical field together and see what we can actually achieve when we work on together, think together, and discuss together. I think that will be very fruitful collaboration between all of us. So today, my topic is cognitive math, and I will, as the title says, I will basically cover two parts. One is what's really a cognitive map, what do they represent when we say a bunch of neurons representing a cognitive map. And the second thing is we're going to talk about some neural mechanisms, neuroplasticity mechanisms about how a cognitive map are potentially formed and constructed in the brain. So that's the two topics of today's basic lecture. And in a few days in the advanced lecture, I will talk about some related topics, including the geometry of hippocampal representation and the evolution of this representation through learning. And we will talk about some abstract representation of task structures and how it may support some inference tasks in animals. And lastly, we'll also talk about some recurrent neural network models with next token prediction that may provide some insight of our experimental data. So now let's get to the, as I said, please interrupt me anytime in the middle of my talk if you have any questions, and I really enjoy discussing with you guys. And also, because I'm an experimentalist, basically, so one good thing for my lecture is I will not have very complicated mathematical equations in my slides. So it should be easy for you guys to follow. I have some mathematics, but I think all high school level mathematics, so should be easy to follow. At least I think so. Okay, so first part, what is a cognitive map? The concept of cognitive map actually originated from a fierce debate between different schools of psychologists to the early 20th century, like 1910s, 1920s, 1930s. And at that time, the most popular view in psychology about cognition or about animal learning is what we today call behaviorism. So behaviorism means those people think everything about learning is just a stimulus response paradigm. Like the animal sees some stimulus, receives some sensory input, and decide to do something, take some actions to get the desired results. And this famous guy, Edward Thorndike, if you guys don't know him, he's really a giant figure in psychology because he discovered what we today call outward conditioning or instrumental conditioning. And Thorndike said, and I quote, in the first place, most of the books do not give us psychology, but rather a eulogy of animals. They have all been about animal intelligence, never about animal stupidity. So as we can see here, what Thorndike worked on actually what we think very smart animals can. Like he put cats in those puzzle boxes and train cats to escape this puzzle box. So we think that this cats are really smart doing this very complicated stuff. But in Thorndike's eyes, all animals are very stupid. You see, he thinks psychology should be about animal stupidity, not animal intelligence. Because in his view, every decision making is just a stimulus response pairing, and every learning is just a complete form of conditioning. Like basically, to associate a certain type of stimulus with another stimulus that Pavlovian conditioning, right? And or the association between a certain type of action to a certain type of stimulus. That's the operant conditioning. But there is another school of psychologists around the same age who really disagree with behaviorism. So this guy, Edward Tolman, he actually coined the term cognitive map. And this is a really famous study from Tolman, which provide an insight of insights in animals. So the paper is titled Insight in Rats. And what Tolman called insight in rats is something like this. So this is what we today call Tolman detour class. So in this class, the animals, the rats, start from this starting box like here, and they need to find the goal location, which is the food box. And as you can see here, there are 3 different ways to get to the food box. But quickly after the animal, after a few seconds, when animal is bored with this environment, the animal quickly figure out that the shortest path is the middle one, right? So that after the extensive training, the animal will always choose the middle one to get to the food box because that is the shortest one. But then Tolman did something very interesting. He blocked some pathways suddenly without training the animal. So, for example, if you block this part, this block A, have a barrier here, the animal first still try to go through the middle one, right? But quickly realize that this is blocked. I mean, he cannot take the shortest middle path. And then the animal quickly, on trial 1, on the first trial, when after animal realize that there is a block, you will go back to the first choice point and then turn left. Because now, as you can see, this is the optimal solution to get to the food box, the shortest one, right? But if instead you put the barrier at block B location, then you will then go back to the first choice point, not the second one, to the first point, and then turn right, because now this is the only pathway that you can use to get to the food box. And this completely contradicts with Thorndike's idea that everything is a law of effect, meaning you just keep updating your actions based on your outcome. Because if that is true, the animal needs to do another round of trial and error to figure out which pathway is the optimal one, right? But instead, even on trial 1, the animal can do it, can make the correct choice.
But the animal explored the environment
before, yeah, exactly. So I don't remember that details. A few days, how many days, I don't remember. But yeah, that definitely require pre-training of the animal within this environment. Yeah. So based on this observation and many others, of course, Tolman invented this term cognitive map because he's like this data, this behavioral observation indicate that the animal actually have a map of the environment in its mind, right? So that's why when some pathway is blocked, you can actually mentally simulate which is now the best pathway, the optimal solution, and then directly choose that solution without doing another round of trial and error. So that's why he said this is a cognitive map, and he said this means the rats have an insight. That's the term he used. So what Tolman called insight here is what we today typically call model-based learning. So this is if we use today's reinforcement learning language, so this means the animal doesn't only learn a sequence of actions. So that's Thorndike's idea, right? But instead, in the pre-training session, the animal learns the structure of this environment. So that's a model of this environment. So after that, the animal can do mental simulation with this model and do a very quick inference. And after Tolman's idea, of course, many different people can look at which part of the brain may be responsible for forming this cognitive map or model of the environment. And two of the most proposed brain areas for cognitive map so far is one is hippocampus. There are actually pretty extensive evidence showing hippocampus represent cognitive map. The other is orbital frontal cortex. I think there's also some evidence showing OFC has something to do with cognitive map. But of course, not limited to these two brain areas. You may see many different other brain areas showing similar activity patterns. Okay, so what's other evidence that this hippocampus has evolved in the model-based learning? For example, this very famous Morris water maze is part of, you may know this behavioral paradigm is from Richard Morris. And in this behavioral paradigm, there's a hidden platform in the swimming pool. And the rat can swim, and there's no problem for them to swim in the water, but they don't prefer to do that. They want to keep dry of themselves and find that hidden platform. And after training, you can see that the animal can actually quickly find the hidden platform. And this is a test actually where the platform is removed. So the animal still goes to the hidden platform location and search around because the animal thinks there should be a escape hidden platform here. And why we think this is evidence for model-based learning is because you can actually train the animal during the training process. You can actually train the animal from several different entry points in this water maze, but test them with some novel entry point. So because if you don't do that, if you keep training the animal from one single point, it could be really model-free. The animal can just learn a direct trajectory, a direct path swimming to the hidden platform. But because you are keep changing the entry point, and you are testing with a novel entry points, then you can still do it, can still locate the hidden platform. That's sort of behavioral evidence to show that animals have some ability of model-based learning. And of course, when you listen hippocampus, the animal this will dramatically disrupt the animal's learning process. Right, but this someone thinks is not very rigorous, right? Because you can argue that even with no entry point, the animal maybe during the training section, during the exploration section, the animal actually have been that place before, right? During this searching. Right, so after that, people develop different types of behavioral paradigms to test model-based learning. I'm going to show you one recent one, actually not so recent now, but still more recent than Richard Morris study. This is from Kevin Miller, the one who worked with Charles Brody. This is what we call a two-step choice paradigm. So it's two-step because initially the rat need to choose the left or the right nose toe port from the upper row. So that's the choice point. So the animal choose either the left one or the right one. And based on the animal's choice, there is a certain probability that this state will be reached. So if the animal chooses the left one, there is 80% of chance that you will get into this purple contact, this purple state. But there's another 20% of chance that it will get to this pink state, pink context. And it's opposite if the animal chooses the right one, right? So the animal can make a choice for get to one of this state, one of this contacts with high probability. And this is step one, this is the choice step. But after this choice step, the second, there's a step two. The second step, there's no choice at all. So the animal just make one choice in step one, no choice in step two. But in step two, is if the animal is in this purple state, it's always at the left port, left lead port on the bottom row have water, have one certain probability to have reward. For example, 70% of chance have a reward, 30% of chance have no reward, right? But if the animal is in this pink context, the pink state, there will be, for example, 40% of chance to get a reward, 60% of chance to get no reward, right? And why is this behavioral paradigm can test whether the animal use model-free learning or model-based learning to do the behavior? This is because we should consider that what happened to the animal when it didn't get any reward in the last one, right? So when the animal chooses something and there is no reward coming out from the lead part, should the animal just evaluate the last choice if there is no reward? If you are learning in a purely model-free manner, you should do this, right? Because this is the law of effect. you take one action, you get nothing, you get zero reward, right? Then you should reduce the probability that you take the same action, right? So then the animal should really do this. But if the animal learns the task structures shown here, the real task structures, whether this question is yes or no should depend on whether it enters this state, this purple state, or this pink state, right? Depends on which state the animal enters after the choice point. For example, if the animal here make a left choice, but actually because there's even when the animal make a left choice, there's a 20% of chance to get into the right state, right? So if the animal make a left choice, but get into the right state and didn't get any reward, then if the animal really learns this structure, this model, it shouldn't devalue this left choice action because it knows it's just some rare thing happened, I get into a different state, right? So based on this kind of analysis, the authors can discriminate between model-based versus model-free learning and test different brain areas that has been previously thought to be involved in cognitive map, whether they are indeed involved in model-based learning. So they use autogenetics, maybe mucinol here. They use mucinol to silence either orbital frontal cortex or dorsal hippocampus and quantify what they call a planning index as how model-based learning it is planning. And as you can see here, so compared to the control condition, in both conditions where you silence either hippocampus or OFC, you have a reduced planning index. So that sort of indicates that both brain areas is indeed involved in model-based learning.
Two states switch back and forth.
Back and forth, right.
For the blocks.
For the blocks, yes. So yeah, here, you see that there's a keep reversing the probability of the reward probability in this good things. Okay, so there is some behavior, as I showed, there is some behavioral evidence showing the hippocampus or some other brain structures indeed is involved in model-based learning, and we think at least if we use Tolman's language, they represent cognitive map. But what is really a cognitive map? Can we give a definition of that, right? So before we get into that question, I want to first talk about what is not, should not be the definition of a cognitive map, right? What should not be the definition of a cognitive map? It's a very strict understanding that it has to be a physical map in our living, Euclidean space in this world, but the representation of this spatial map in the brain. I'm not saying the spatial map of this world is not a cognitive map. It is definitely one, but we should not think that it has to be a spatial map for us to call it cognitive map. Or we shouldn't think like those brain structures like hippocampus or OFC is only responsible for spatial navigation, right? I think that is definitely not correct. Showing you a few examples. A very popular study from Howard Eckenbaum's lab doing this delay match to sample task with olfactory cues. So this is a head fixed rat. So the rat is not moving at all. Its head is fixed on the experimental rig. And then there are different odors delivered to the rat. There are basically each shot there are two odors delivered to this rat. And the rat needs to make different choices based on whether these two odors match with each other or not match with each other. So this is a very classical working memory task, they match to sample task. And as you can see here, so all those figures are each row is one neuron reporting from dorsal hippocampus. So obviously there is no spatial navigation at all. There is no spatial component whatsoever because the mouse is completely fixed. But you see very nice play-style-like sequence in dorsal hippocampus. Also depends on different cues, different olfactory cues. And this figure on the right is one study from Dmitry Aronov. Now he's working on a bird hippocampus. So, the x-axis you can think it as time, but this is the theta cycle, but basically time. And each row, the y-axis is neuron. Each row is one neuron. Okay, so this means so the neural population becomes high over this delay period.
include the effect of, for example, eye movement.
Eye movement. So first, this is an olfactory part. Eye movement shouldn't directly affect the sensory part, right? Also, even there is some eye movement. I mean, my point is there is no spatial navigation. Even if there is some eye movement, it's still not spatial. Yes. No, yeah, I just talked with New yesterday. So in 2014, you guys probably know Zhao, Hopfield, and Mosers, they got Nobel Prize for their discovery of play cells and grid cells. I think it's totally deserved. No doubt about that, right? Because it inspired the whole field to study this. But the problem is, what do you give them the prize for, right? Because if you check Nobel Prize committees comment, they say they give them the Nobel Prize for their discovery of a GPS system in the brain. I think that's very misleading. I mean, I'm not saying hippocampus is not, or FDC is not doing spatial navigation. Definitely play an important role in spatial navigation, but that is just one very specific implementation of a much broader function of hippocampus and MEC. Okay. And yeah, on the right is the Richard Arnold study. When he worked as a postdoc in Compte, he is now working on bird hippocampus. And I encourage everyone, if you are interested in hippocampus, check out his written works in bird. But at that time, he's still working in the rats and rodents with saving time. And as you can see here, this is the pure auditory part. So the rat is trained to push down a lever, and then a chirp of sound will be played. I mean, with ramping frequency at different speed. And the rat is trained to stop, to release the lever at a certain frequency to get a reward, right? So as Eichenbaum's paper, very obviously this is not spatial navigation, right? It's not a spatial task, but you see a nice tiling of hippocampal activity during this sound playing period, right? So it's also showing you hippocampus not only for spatial navigation, and I'm going to, so those two are pure non-spatial tasks, right? So now I'm going to move on to some spatial tasks. I mean, it looks like spatial, but if you add some non-spatial component to this spatial task, you will always see that hippocampus is not only representing the spatial information, even though there is pretty strong spatial information in this task. For example, in this 2020 Pangala paper, so the rat, I think the mouse is trying to use this 4-lap reward collection task. So basically, there is one reward location, but the interesting thing is this reward location doesn't always have a reward. The mouse is running around this circular arena in cycles, right? And only get one reward for 4 laps. So 4 cycles, 1 reward. Okay? And you start to see some cells. They have spatial information because they have a specific firing field and a particular location in this circular arena. But their firing rate, their firing preferentially occurs when the animal is in a certain number of laps counted from the last reward, right? So for example, this cell preferentially fire for lap 1, in lap 1, this cell for lap 2, for lap 3, and for lap 4, right? So those laps of activity, so all those cells have a spatial selectivity, right? Obviously, but they also have a very non-spatial selectivity for the lap numbers. And another paper from Chang's lab, when they do this, what were the evidence accumulation task? So in this time, it's a virtual reality, so this mouse had fixed in a spherical treadmill. And in the virtual environment, the mouse is running down a linear corridor, and at the end, there's a branch point, so the mouse can choose to turn right or left. But so how should the animal decide which turn to make? It's along this central arm, this linear corridor, there will be some objects you can see either on the right wall or on the left wall appearing at random locations along this linear corridor. And the animal actually needs to count whether it encounters more objects on the left part or more objects on the right part, right? So accumulatively. And at the end, at the choice point, if the animal sees more objects on the left, it should turn left. If it sees some more objects on the right, it should turn right. So this is the evidence accumulation task. So in this task, there is a spatial component, meaning like which position of the animal is in this virtual linear corridor, right? But there's also a non-spatial part of this task, which is what's the stress of the evidence basically correlate with if you count the number of left objects and minus that with the number of right objects, what's the difference between the two, right? So and they also find very interesting thing is each individual hippocampal cells conjunctively encode these two spatial and non-spatial elements. So clearly, even in this spatial task, when you add some task relevant non-spatial information, the hippocampus is encoded. Okay, so hopefully I convinced you that hippocampus and the related MEC system is not only for spatial navigation, right? So cognitive map shouldn't be understood as just a spatial map in the brain, right? So then what is so just briefly mention that, so if you are interested in some computational theory about how to bring these two parts together, like spatial information encoding and non-spatial information encoding, and how to unify these two seemingly very different things under one single theoretical framework of relational memory, I encourage you to check this paper from James Whittington and Tim Barrows. They made this model called Total Eigenbound machine. For the sake of time, I don't think I will have time to discuss details about this model. It's basically using a generative model by a recurrent neural network to predict what should be the next sensory cue that you will encounter after you take a certain action. But then, if you are interested, you can read this paper. Okay, so let's get into this. I think really interesting, but sometimes misunderstood question about what should be the definition of cognitive map. We think that from the very beginning, like I said, Tommy invented this term to describe something in model-based learning, right? So it should have something to do with model-based learning. And in reinforcement learning, the model is referred to as the state transition probability matrix of the environment. So basically, it's the probability of the next state and the rewarding that given the current state and the current action you take at this state. So in machine learning, in reinforcement learning, if you know this, we say you know the model of the whole task. And you can use this model to do planning for whatever goals that you have, right? And so obviously the cognitive map, the concept of cognitive map needs to be related to this concept of model in reinforcement learning. But how? Like, what definition should we give to this term, this cognitive map term? Yeah, unfortunately, I wouldn't say I have definite answer to tell you, because like if you ask 100 different neuroscientists, they will probably give you 100 different answers. But I think it's important because if you a very unfortunate trend I think nowadays is people start to use this term more and more loosely, and like some people just, for example, just give you an example, some people just get into a random, some brain areas record their neural activity, and as long as they see some spatial tuning when the animal is exploring an environment, they say that brain area will represent a cognitive map. So if you start to do that, you will probably find a pretty nice cognitive map in retina, I guess, if your environment contains some very salient visual cues. But intuitively, we think it will be very odd, very weird to say a retina represents a cognitive map, right? So what's the definition of this? Because we definitely need a definition. Otherwise, you can end up with arguing with other people for an hour without actually disagreeing on anything, right? So I didn't say this hypothetically. Believe me, it happened in my life a couple of times before, actually. So although I cannot give you a correct answer that approved by everyone, I think even a wrong, not really wrong, even a bad definition is better than no definition, okay? So I will read this. So when I prepare this slide, I think, okay, what is my definition of cognitive map? What I think is the key features of cognitive map, right? So I think if I will call a neuron example called a cognitive map if the activities of individual neurons in this example correlate with some variables. I try to make it general, okay? So correlate with some variables related to the transition probability from the current state to some future state. And in this sentence, of course, the key concept is state here. So what is the state? So I think each state should be determined by the instantaneous and past sensory information and the animal's actions, often conjunctive with multiple factors together. So I try to keep the key concept here, key features here, but also make it as general as possible. So I don't exclude many useful thinkings, many insightful thinkings in this field. So basically, what I mean is something like this. So the firing rate, so if I use Rn as the nth neuron firing rate, it should be a function of the current state and the current action. And with some parameter set, theta is the parameter set of the Rn, of course. And we say within the parameter set, you can have whatever parameters you like, put whatever parameters you like into this set, but it has to contain some specific state. So why do we need to contain that state? Because then within this firing rate should be a function of state transition probability from the current state to some future state. If the future state is some particular state, some specific defined state by this parameter, right? By this what I call S theta parameter. And of course, there is no reason to say we should only consider one step forward. You can consider 2 steps forward, 3 steps forward, whatever. Right? So I say some future state. I can say has to be the immediate future state. And also, we need to exclude some very, very trivial choices of this function f, so that although you write a formula like this, but everything cancels out. Eventually, it has nothing to do with the transition probability at all. And that's so trivial. Of course, we won't call that a cognitive map, but I didn't require a one-to-one matching, a unique mapping from the transition probability to some certain firing rate. We will see why we do that, because sometimes you will see hippocampus is encoding something related to the transition probability, but not directly is the transition probability. Okay.
2 questions. One is you say it's the 2 solid states.
Yeah.
So, but a given state. So you say, for example, being at some position.
Being at some position,
But,
yes.
Okay, but then one neuron would then correspond to a pair of state action and state, right? Because if you transition.
Right. Yeah. Some variables related to that, right?
Okay, so, but for example, brief set or plane set, it doesn't seem like they fall into this category.
I think it does. I mean, I'll talk about that later. How play style representation can fit into this concept. Yeah, because the traditional way to think about play style is you just calculating the distance between your current state to a given state, right? So even that traditional view can fit into well, that not fit into this concept because there's no probability, right? But I'll talk about that. That is actually a very key part of this lecture later, like how we can fit play style, change the traditional view of play style to fit into this framework. Yeah, the reason I really need to have this transition probability here is because if the whole concept originated from model-based learning, by definition, what you want to have a model, you need to know the transition between different states. If it's not transition between different states, it's not really a model anymore. Right? It's just isolated representation of different states. And yeah, and by state, another thing is what is really a state, right? So by state, I mean it has something to do with your sensory input, of course, but also the past sensory input and your past actions, your past trajectory, basically. So why do I mean that? So yeah, so as I said, 2 key things here. So one is what is a state. Second thing is what do I mean by some variables related to the transition probability. That's the 2 key parts. What are the questions?
Why do we reward in this model that when we consider performance task in the pre-training stage when the rat feels like a mixed map, there's no reward.
There's a food box. That's a reward. We need a goal here.
For more natural conditions,
Yeah.
there's not always rewarded in some environment. So but we can still build up our connecting back. So why the reward doesn't make sense?
Sorry, yeah, good question, very good question. Actually, later I will talk about the separation of this two part. I just want to, as I said, I want to make it as general as possible. So I want to have this reward term here, but of course you can separate this into two probability, right? So ST plus 1 given ST and AT, and RT given ST and AT. You can separate this into two probability, and you can say only care about one part, didn't care about the other part. That's fine, and that's actually pretty useful in some tasks, in some flexible planning tasks. So good question. We'll see that later. But I'm just saying you could include in some scenario at least it could include reward because that's anyway a very important information on this of any environment, right? Yeah. So two things. So what is really the state? What do I mean by transition probability between different states? So if you really think about this concept state, okay, question.
Difference or the relationship with as I know that one model is the response of the environment of
Yeah, good question. So yeah, I think different people may define it in different ways. Yeah, in machine learning, mostly we talk about the state structures, right, as a world model, right? But yeah, as I said, reward. Yeah, one thing is if you don't change actually you in model-based planning, you need to know the goal to plan, right? If you don't know the goal, even if you have the environment states, you don't know how to plan a trajectory. So either you separate this reward part into a different term. Okay, you say we don't call it cognitive map, we call it reward map or whatever. That's your choice. But I just want to say that this should be part of information that you care about when you do this task. And later, as I said, later I will show some examples that I think some thinking that in some cases the reward can be separate from the state transition probability. Right. So, but first, I mean, what is a state, right? So if you really think about that, it's not that trivial because what we call state is really a latent variable. I think the brain created itself to facilitate learning. It's not an objective thing in the environment because in the environment it's only sensory information. It's only sensory cues. Actually, if you take the behaviorism view of point, you can directly go from sensory cues to actions, to decision making, right? You don't need any latent variable in the middle, right? And in fact, a lot of tasks doesn't require hippocampus or doesn't require intermediate variable, a latent variable called state. For example, if you just train the animal to do this pure fear conditioning, meaning you have a pure tone and play a pure tone and push out the animal, and the animal will freeze after hearing that pure tone. If you just do that, it's totally hippocampus independent. And if you do some simple visual discrimination task, it's totally hippocampus independent. And if you even want to do some spatial navigation task, if that task is simple enough, for example, spatial alternation, meaning you just train the animal to turn left, right, in alternating ways in a double shape, a figure-8 maze. Animal would show that without any delay, meaning the animal can continuously run around the figure-8 maze without any holding chamber at the start point. If you do that, animal would show that the vision figure times animal speed. So no need of something in the middle called state. But it could be helpful in some cases. I think there are multiple advantages for having create this latent variable that we call state. So I will just give two examples, which I think is the most important thing. So one thing is hidden state inference. So
this is very complicated. In the expression, the two-step decision.
Right.
Yeah. Then the experimenter is implementing this.
Yes.
So you had pink and you had purple.
Yeah, but then of course animal didn't see pink or purple.
But then the animal can infer some probability
Exactly.
over those states.
Yeah.
So the states are
actually real.
Yeah.
So they're done by the.
But the animal is operational. That's actually one good example of hidden state. So hidden meaning is not explicitly given by sensory cue. Right? The animal is not cueing the animal which state we are in the past.
No, right, but so, my understanding is that it's different to say that you have two objective states, but you don't know them and you have to infer the probability that you're in one state or the other, versus saying I can create any latent variable I want in my mind as a summary of something. And they might not correspond to anything that exists objectively. And they might be useful for me to do computations.
So what I mean here is it doesn't correlate with anything instantaneously at the current moment in the environment. But you could correlate with something based on your past experience. So for example, the thing is, so all the theory, at least the one developed by Richard Sutton, right, is based on Markov decision for the time. Has to be Markov, has to be independent of history. But in the real world, all cases is dependent on history. So for example, I'm at this place, but what should I do? Depends on whether I come to this place from the left side or from the right side. If I come to this place from the left side, I should do one thing. If I come to this place from the right side, I should do another thing.
I don't want to put it on too much. I think that's a completely different issue. But there's an objective state, which is the position you're at.
Right.
You might not know it, but it exists. Right?
Yeah.
It's not just a latent variable that my mind constructs. That's anyway, maybe I will understand.
Yeah, so what I mean is, so sometimes the brain needs to split one objective state into actually different states. For example, you can say this position is one objective state, right? But in some tasks, if it's history dependent, the brain needs to split it into multiple different states, right? So that's what I mean here. Yeah, I'm happy to discuss with you later about, because I didn't fully follow your arguments. Yeah, here, I think what I mean is like, in many real world tasks, you need to really create some latent state or hidden, infer from hidden state, not based on your current observation, but based on the history of your observations. So we typically call this hidden state inference, and we think cognitive map is good for doing that. For example, this is actually two groups published very similar things in one issue in Neuron. So one from Emma Wood in Howard Eckenbaum's lab, the other from Lauren Frank, at that time working with Matt Wilson. Both papers published in 2000. And just one example of this was so-called splitter cell, meaning when the animal is running, doing this actually spatial alternation task, left, right, turning in this figure 8 maze, you'll see, if you record from hippocampus, you'll see many cells, they are play cells in a way, but their activity are dramatically different when the animal plans to turn left versus to turn right? So they call it splitter cells because those cells, they think, split one single position into two different states, depending on the animal, whether the animal plans to turn left or right? And you see modern version or more recent version of this splitter cell phenomenon. This is my colleague's work in also Sprucen lab from Weinan, and what he showed is if you train the animal to, in virtual reality, to do this topic, animal first see two different indicator cues, and based on the two indicator cues, decide whether later on in the linear corridor, the first cue position has reward, or the second cue position has reward. Right? So after the indicator cue, everything looks the same. So the animal sort of split the space in the later talks to based on the previous indicator cue. And using completely separate representation, nearly orthogonal representation in hippocampus after the indicator cue, or depending on the indicator cue. And I also used this paper from Max Field's lab showing if you do reversal learning paradigm, training a mouse to either leave the left lead port or the right lead port, sort of reverse the reward probability between this lead port, then you can actually infer the hidden state. Here, the hidden state means whether you are in the left rewarded context, left more rewarded context, or in the right more rewarded context, right? So you have separate representation in the context to encode the two different contexts. So that's one thing that is good for the brain to have a cognitive map that have the ability to hidden state inference. Another thing that can be beneficial from having a cognitive map is generalization. So I borrowed this figure from Stefano Fusi I think this is a really nice illustration of what generalization means here. So for example, if you go into different countries, because in different countries, in some countries you drive a car on the right side of the road, some countries you drive a car on the left side of the road. So when you cross the road, you should, for example, if you're in UK, because they drive they are left driving countries, so you should look, when you cross the road, you should look right first. And if you're in the US, you should look left first. And this doesn't matter whether you are in the city of in that country or you are in the countryside in that country, right? So you should always do the same thing. And so you need some. So what generalization means here is like regardless of the sensory details, whether you are in the city or in the countryside, you should always do the same thing, right? You should have the same classification. And there are different ways of this for this generalization to happen. The first is so if you have a cognitive map that completely merges these two different states, right? So you say it doesn't matter whether you're in the countryside or in the city, as long as you're in UK, you have one label that as one state. If you're in the US, I label that as a different state. And of course, you can do the generalization easily, right? Just one decoder to separate these two parts. Or in another way, if you still want to keep the city versus countryside sensory representation, you can merge these two points, not completely, but along some certain dimensions, and you can still have a good generalization. And this one is an abstract representation. For example, here in this panel B is you can see the city versus countryside are still separate from each other to keep this information, but it's along an orthogonal dimension compared to UK versus US axis, right? So you can say, although strictly speaking, everything is still separate, but along certain dimension, you actually merge city versus countryside representation, right, along this dimension. So this is also good for generalization, and I want to, for the sake of time, I will speak all in details, but they actually did some human reported experiment to show that if humans are doing inference tasks, they actually start to see this generalization pattern, abstract representation pattern, good for generalization in human hippocampus. Okay, so yeah, so that's first thing. So we talk about why we should have a cognitive map in our brain to create or represent the latent variable state, right? But the second thing is, so we didn't, as I said, we didn't separately represent different states in a very isolated way. We care about the state transition probability from one state to another, right? So because that's good for model-based learning. So when you have this transition probability, when you have this model, you can apply different methods that engineers and mathematicians develop to do planning, to basically mental simulation of what you need to do in the next trial without actually doing that in the real world, which could be time-consuming and risky, right? So still, I don't want to go into details about how to do this, but there are very established ways in reinforcement learning. When you have a model to be planning, for example, you can do dynamic programming to keep iterating, optimizing your policy function, basically what you should do, and your value function, basically whether you are in a good state or not good state, right? Which state has the best value, you can do a closed loop optimization of these two things to eventually get to the optimal policy to know what to do, right? So that's the model-based learning. But as a comparison, of course, you can have a way of model-free learning. So there are multiple. very diverse repertoire of algorithms for model free learning, but one very basic way, or one of the basic ways to do this is to have a representation of each state's value. Okay, so you create a function called state value function to each state. Basically means when you are at this state, what's the expectation of total reward that you can get in the future? Okay, so this is basically a mathematical expectation of future reward in a discounted way. So this gamma here is a discounting factor. It's a factor between 0 to 1. Here you see it's just a summation of all future reward, but the near reward is weighted higher than the distant reward. And this is, I think, also very intuitive because if I say I want to give you $100, you will prefer me to give you this bill now instead of in 10 days. Because in 10 days I may escape or run away and you may not able to find me, right? So even with the same reward value, you will prefer a near reward versus a future reward. So you discount all the future reward, add them up together, and you calculate this expectation of the future reward as a state value function, and then you can come up with optimal policy to go from one state to another state, basically searching for which next state give me the largest value, right? And that's a way of, at least one of the ways to do a model-free reinforcement learning. And this tool, if we compare these two models, these two ways of basic algorithm for reinforcement learning, whether you require a model or don't require a model. As I said before, you may think that the model-based learning is really great. It's always better, right? So because when you have a model, you do manual simulations, you do planning, you don't need to redo trial and errors when the reward changes. You have a very flexible planning ability, right? But actually, for example, for me as an experimentalist, if you spend some time training animals, you will quickly realize that it's actually really hard to train an animal to do a model-based learning. I mean, that cross-study with Kevin Miller, this two-step task actually requires a pretty extensive training for an animal to get it. Okay, so if this is really good, why don't the animal always do that, right? If there is no drawbacks of it. The problem is that it's really hard to keep a model. I mean, this is very computationally expensive. I mean, you need a huge amount of computation to actually accurately know what is the reward what is the state transition probability. It's first very hard to compute. It's also very very demanding to store all the information. Okay, yeah, after this line, yeah. So that's why in most cases, actually when you train the animal, at least when you over-train the animal, when you extensively train the animal, you start to get a habit of the animal, not really a very intelligent learning or decision making. You can still call it decision making. That's always your choice of word, but it's actually just the animal just form a habit. And when the animal forms habit, almost everything is model free. Animal just do very stereotypic behaviors after seeing certain stimulus, right? So those two things should be at two extremes of the whole spectrum. Right? On one end, you have this very flexible but very computational demanding model-based learning. On the other hand, you have this very stereotypic model-free learning. Is there something in the middle? Is what we think is interesting, and many people say interesting that a brain may do, like sort of to strike a balance between these two. Right? That's how the way I will talk about that. Yeah, thanks for all the questions. And yeah, so as I said, the pure model-based learning versus the pure model-free learning, as for example, when you create a state value function and use, for example, temporal difference learning technique algorithms to learn a accurate representation of return of expectation for each current state. This is the pure model-free learning. They both have their advantages and disadvantages, right? So is there some way in the middle that can sort of strike a balance between these two? So for this, I'm going to introduce the theory mostly based on this paper. This is from Kim Stachenfeld when she worked with Matt Bovinick and Sam Birchman in Princeton at that time. And she's now doing her onward at DeepMind and Columbia University. And also she published a bunch of very interesting papers, very inspiring papers. I think so we encourage everyone, if you're interested in this topic, to check Kim's paper. And this paper introduced something called successor representation. And this concept is actually not new. If you really check the literature, you will see that Peter Dayan proposed that he would transform sort of a successor representation in 1993. So it's actually a pretty old concept. But in 2017, Kim and her collaborators actually revived this idea, or modernized this idea, and show some very nice simulations or correlations with a lot of neural activity data. And as you can see here, like the key point for the successor representation is that the cognitive map should be a predictive map, meaning to predict what future state, the future occupancy of each state that you will be from the current state, based on your current policy function. So what is the successor representation? As I already showed you, if you start from the pure model free learning part, we define the state value function as V of, it's a function of the current state, but also depends on the policy. The pi is a policy here, depends on the policy. It's the expectation of future discounted reward, right? It's the data of future discounted reward. And let's separate this term into two parts. So basically, as one student asked me in the last session, can we separate all the variables, all the calculations about the state from all the calculations about the reward? Right? Can we factorize this two parts in separate terms? And indeed we can separate this expression into two terms for the state value function. We can calculate first. So we can separate the reward from each different state to like this function. This is, as you can see, this is actually a discounted summation, actually a discounted counting of how many times you will be at a certain location in the future, right? So this established cursive I here is just a counting function. So one big T is actually some future time after a small t. Okay, so one st equals to s prime, you count this as 1, meaning you get to that location once, right? So if it is not s prime, you count it as 0. So this is basically a counting function, and you do a discounted counting of a particular state in the future and add them up, and you get this, and you do the expectation of it. This is basically an expectation of future occupancy of a certain state from the current state. And this is obviously a variable of the current state and a particular predefined future state as prime. And if we call it M, ST, and S prime, this is what we call successor representation. All right, and we can separate this value function into a successor representation and actually the reward of each the reward in each future state, in each S prime state. And from this, we actually achieve something that we can flexibly change one part, for example, the reward part, without the need of relearning all the state transition probability. Right? Because you can imagine that if your goal changes at some point in this task, you just need to change this R to reward of S prime. You don't need to change this successor representation. There's actually no change of the state transition probability to each state. Okay.
How is this mapping to cognitive map?
I'll show you in the next slide. So yeah, so this is, yeah, I will quickly go through this one. This is just basic illustration of how you can achieve a flexible reward recalculation, right? If your reward changes not reward recalculation, value function, state value function recalculation if your reward function changes, right? So as I said, you just keep the philosophical representation, multiply with a novel reward representation, and you get your value, state value representation. Right? And yeah, as you asked, how is this related to one more is so you can see why SR is somewhere in the middle between the pure model-based and the pure model-free learning, because in one way it's still model-free because it doesn't explicitly encode the probability of every state transition, every pair of state transition, right? It still depends on your policy function. The state value function depends on your policy function, because if you change your policy function, basically means you make different decisions at each different state, and of course each state will have a different value. And it's actually the same here with successful representation, because if your policy function changes, you will actually have different future future occupancy of each state in the future, because you make different decisions, right? So in this way, it's still sort of model-free because it still depends on the policy function. But in another way, it can, as I said, it can achieve flexible recalculation of value with dynamic nodes, with a changing reward function. So in this way, it's not as stereotypic as a model-free learning result. In this way, if you change the reward function, you redirect it. You need to redo the whole process of trial and error. So this is the SR is somewhere in the middle. And how this is related to the probability map? So that's a key thing in the 2017 PIMS paper, right? So in this paper,
the simple representation assumes that Xinyu is trying.
yeah.
So in that sense, it's model-based, but the model-based also requires a policy.
The model itself doesn't require a policy, but to planning based on a model, you need a policy.
Yeah. So in what sense is that different from model-based?
Because the reason is because think about that. So if you change the goals. So first you need to First you need to recompute the value, right? But after you recompute the value, you need to do some computation. You need to do something to recalculate, to relearn the policy function. You cannot directly, so without interacting with the environment, you cannot directly update your policy function. No. The model is meaning all the transitions. Basically, you can simulate everything in your mind. You don't need to actually do that. Because if you have all this probability, you can just think about the environment. Okay, at each state, if I take this action, where will I end up with, and do everything. Because the successful representation doesn't explicitly tell you if I start from this state, if I take action going forward. Yeah.
You don't know the reward.
I don't think that's
But you say
for the successful representation, if I want to know, I'm probably at this state, if I move one step forward, which state will I end up with? SR doesn't tell you. SR doesn't tell you that. It just tells you what's the probability of your future occupancy in. Because you sum up all those, right? So you add up all the future occupancy.
that's what you need to stimulate, right? You don't. I mean, if you know where you'll end up, you don't need to know what right?
Sometimes you still need to know each step, right? Why not?
It seems to me that the difference is that you separate the reward. So in the successor computation, if you go back one slide, you assume that you know the first condition, but not the second. Correct? So
Yeah, that's a separate thing.
you need to probe the environment to learn about the second condition.
Oh yeah, that's something one thing you need to do. Yeah, no
Maybe
problem.
that's the difference.
But But I don't think that's the only difference. That's of course one difference. Yes. But I think I think one thing is you here this tells you which is your next step, which is your next step. This doesn't tell you which is your next state. This just tell you what is the total probability that you will end up with that state in future until the end of that. Yeah, that's true. Yeah. Yes. Yeah, but it's just not completely tell you like each intermediate step, right, in the middle of this whole trajectory. Right, so how is this related to cognitive map? So this is, I put this toy model just as a illustration of play cells. And you can think each row as a play cell in the hippocampus, and that's their activity. So if you sort all the play cells based on their peak firing rotation, you can get a map like this. And the traditional view of this is each play cell encode the distance between the current state to its preferred state, to its peak state, right? You can say, okay, for this cell, you'll see the firing pattern like this is because it's measuring how far the current state is from this peak state. Right? You can think play cell in this way. But for successful implementation, you actually can get precisely the same picture, but just frame it or understand it in a different way. You'll say, what is the, as I mentioned already many times, what is the discounted future occupancy from the current state to each given state, right? So if it's just as simple as this, these two things are equivalent with each other. There is no difference because you can think about this cell's activity not as a measure of Euclidean distance between two states, but as a probability of future occupancy between two different states, right? From one state to another state, right? So that's just a way of understanding this play cell firing rate of cognitive maps based on the successive representation point of view. But of course, if everything is equivalent, then this is really just, again, you don't need to, you don't actually gain any novel insight, right? But in some scenarios, these two things are actually rather different from each other. One you have, for example, this is case when you have a very strong behavioral bias. So this is actually a very simple case. If you train the rat to run on a linear corridor, but only in one direction, so the rat is trained to only run one direction along a linear corridor, and then you will take a very different path to go back, or you just take out the animal, put it back to the start of the track. Or if this is virtual reality, teleport the animal back to the start. So the animal always runs in one direction, right? If the animal always in one direction, you can see that if you take the view of distance between two states, you will just have a normal shape plane field. But if you think about state transition probability, then it becomes highly directional, because if you at this current state, I have a very high probability to transit into this state, but I have a very low probability to go back, nearly zero probability to go back, because I'm only running in one direction. And the successive representation will predict that in this case, you will have asymmetric plane field that it sort of expand backward from the peak location. You will have plane field ramping up and then sharply going down. And this is exactly what people see when they put rat running in this unidirectional linear track. And actually what's interesting is if you look at day one, when the animal is still new to the track, not familiar with this unidirectional running rule, you see typical symmetric place field as shown in this rat curve. But if you keep training the animal to run unidirectionally for a few more days, you start to see this backward shifting of the place field. This is actually our old study from Meta, and you can, if you're interested, you can check out this paper. So another observation.
So this thing, so this is because so the previous. So no, yeah, no, yeah. So this is because the second line there depends on the policy.
Yeah, depends on the policy.
Now, so if you change the reward, you structure, you change the policy.
Exactly.
So then you would expect that you would change the base.
That's a very interesting question.
Does
Yeah.
that happen?
Yeah, nobody have done these experiments in real life. That's indeed a very interesting question. So one that actually at least a couple of open questions for the implementation becomes that it is exactly one of them. Like when animal change the reward, do you actually see a change of the representation of the countries? Right, so that's the one-dimensional case. Another interesting observation is in two-dimensional. This goes even much earlier, even earlier than this study in history. Robert Mueller did a bunch of studies like this in the 1980s to test what the influence of adding barriers in one environment influence the place field in hippocampus. And as you see here, so if you just put a rat running around this open chamber, this 2D open chamber, and after you record a place field in that rat hippocampus, if you add a barrier in the middle of this chamber, based on different understanding of the place field, you may get different results. If you think the place cell is just encoding a Euclidean distance between one position to another position, you will actually expect to see no change at all of this place field. There is no change in the distance, right? Another way to think about this is that you need to calculate the geodesic distance. Geodesic distance meaning if you add a barrier, you cannot, your counting line, I mean, your distance measurement cannot go through that barrier, right? It has to go around the barrier. So if you think about the place cell in a geodesic distance manner, you'll think that the place field, this side, the upper side of the place field will be cut off. Because now this part has a very large, very far distance from the peak location, right? But then there will be no change of firing on the bottom side. Because there's basically no change of any points on the bottom side to its peak location on the place field. You just basically cut off the place field, right? But what actually happens is, first, you cut off, you indeed cut off the place field. You don't see any firing on the other side, on the upper side, but you also see expansion of your firing on the lower side, right? So this is inconsistent with the Euclidean distance measurement, also inconsistent with the geodesic distance measurement. And the central implementation can explain that because now if you calculate the state transition probability, you start to have a higher state transition probability from this peak location to even a further location to this side. Because the animal has no way to go to the other side, right? So if you calculate the probability, you will have a higher probability on the bottom side. So that's why successful implementation can explain this phenomenon that when you add a barrier in a 2D environment, you don't only cut the place field on one side, and also expand the place field on the other side. And for the sake of time, I will not go through other details in this paper. They show many different examples in hippocampus reporting is consistent with the successor representation theory. And one more thing I want to mention about successor representation is we can actually have a third way think about this place cell matrix, this place cell firing. I thought one way, the traditional one, is to think the place cells as the measurement of distance between two states, and for the successor representation, think about the place cell activity as a discounted future occupancy from a current state to another state, right? And you can also think that maybe we think this place cell activity as a direct encoding of transition probability from the current state to the next step, in the next step to the third to a certain state within a short time window, right? If you discretize your time in different steps, right? And how short it is, like the length of this window is actually determined by the gamma, by the discounting factors when you calculate the successor representations, right? And if you think, so these two are really just equivalent in different ways, saying the same thing. And if you really think the place cell as a direct encoding of transition probability, there is actually one very interesting question is, how do you plan in multiple steps, right? Because in the real world, typically you don't want to plan for one step. You may plan for a very long sequence in the future. Right? I need to go to that location first and turn left, to go to some other location and then turn right, and then go straight. Right? You can plan for multiple steps. Then what you need to do is you need to calculate. You want to know the probability of probability into a certain stage after k step, right? Not just one step. And obviously, to know this, you basically want to multiply this matrix for many times, for k times. Okay? You want to do a k time multiplication of this transition probability. So if I call that M, call that matrix M, so to calculate that probability after k steps, that you are in this particular state, you basically need to calculate this. You need to multiply this matrix by k times, right? And this could be very hard to compute. Right? Multiplication of a matrix for many different times, right? Then generally it's hard to do this, but if this matrix is symmetric, for example, like shown here, so if we ignore the very special case that I only run in one direction, right, and that is a very special asymmetric case. But if a matrix is really symmetric like this, for example, animals running in all directions in one environment, there is actually, I think we all know that there's either easy solution for that mathematically when you want to multiply a symmetric matrix for multiple steps. So we can basically do even decomposition of this matrix, right? We can do this. Let's just call it. Right, we can. So this is the eigen value of this matrix, and this is all the eigen. Each column is the eigen basis, the eigen vector of this matrix. The reason is if this is the probability transition probability matrix is asymmetric like this, all the eigenvectors should be orthogonal to each other, right? So when you multiply this by no matter how many times, every Q invert times Q cancel out with each other, and you just need to this eigenvalue. This is just a diagonal line. So this is basically you just need to calculate. You just need to calculate multiply a scatter for k times, which will be much easier than multiply a matrix for many different times, right? So people propose this idea that is there some case that you can find a representation of eigenvectors of this kind of place field, symmetric place field representation. And if you really calculate the eigenvector of this 1D, this is just a toy model of course, this 1D place field map, you actually get something like this. So each column should be one eigenvector of this matrix, this sort of diagonal matrix with a certain width, where there's a non-zero width. And you can see each column, the key feature here is each column is periodic, right? You got a bunch of periodic functions as the eigenbasis of this place field matrix. And this is of course a simple 1D case, and people think that this may have something to do. I just want to raise this interesting point as what people propose. I need to mention that there is no very strong evidence to show that the brain is actually doing this computation, right? Because even for that, you still need to do a multiplication of a scalar for multiple for k steps. I don't know how the brain can do that. I mean, how could a neural circuit implementation of k step, k time multiplication of a scalar? It's possible that we can do that. I'm just saying, nobody has shown that experimentally. But the idea is the brain cells, those periodic firing patterns that people see in the upstream brain areas to hippocampus for example, medial and parietal cortex, as you probably know, this gray cell discovered from Mozart that may represent eigen basis of play cells. And even if they are not used to do this multi-step planning, they may be good for doing other things. So this is just, I think, an interesting idea that people raised. All right. I think the eigenvalues basically tells you the contribution of each eigenvalue, how important they are, right? And as you can see here, so each column, they have different period, meaning if you look at the frequency of each pattern, it's actually different. So this has a very low frequency, right? And on this side it has a very high frequency. So this actually also correlates with some observations in gray cell. Like gray cell is distributed in different models with different frequency, with different spatial frequency. And then if you look at that eigenvalue, you may see that the largest one actually have the smaller, lowest frequency, lowest spatial frequency, right? So that meaning maybe you should have, if you really want to do this, you should have more low frequency gray cells and high frequency gray cells, which is indeed correlated with people see in their recordings. But of course, that's all correlation. I mean, so far I've seen no experimental proof that this gray cells is really used for multi-step planning on this. I see no evidence of that. But I think this is an interesting idea from Tim Barnes and Neil Burgess to think gray cells as eigen basis of gray cells. Yeah, so as I said, I mean, there are some open questions for successful implementation, although Kim showed many matching experimental data with this theory framework, but many things are different. Not really, many things are remains untested, or may require some future work or future theoretical modification of this successful implementation framework to match with experimental data. One thing is, if you really believe this SR thing, because the key point here is to separate the state representation from the reward representation. But are the two things really separated in hippocampus? There are actually several papers. I think the earliest one is from Compte in 2018. Also, there are some other papers more recently showing that there is actually pretty strong reward representation in hippocampus. So rewards, whether you have a reward or not, whether Lauren Frank also showed whether you have a larger reward or have a smaller amount, smaller value of reward, all those reward related things impact play cell firing in the hippocampus. So that on its face value is of course inconsistent with successful representation, right? Because that requires you to completely separate reward representation from state representation. But of course, you can argue that that's different population of cells in hippocampus, right? Because not every cell in hippocampus is impacted by reward. Right? Some are, some are not. So there might be a diverse population in hippocampus representing different things. Another thing is, as I mentioned, so is there really flexible value recomputation when you change the reward location, right? And honestly, it has never been rigorously tested. So it will be interesting to look at in the future. And I want to mention one more thing is for the cognitive map and reinforcement learning is I talk about model-based learning, model-free learning, and somewhere in the middle, the successful representation. The strategy that animal takes to do decision making and learning are not fixed. It's actually a very dynamic process from the beginning of the learning to the end of the learning, or even with more and more tasks added or training added to the animal. As you see here, I won't go into details about this, but the point is there could be an arbitration between different modes of learning. For example, here is between the sensor representation and a purely model-free learning, model-free representation of actions in the hippocampus or other brain areas. So in this model, this also from Kim and his colleagues, they propose that you can have two parts in the learning system, maybe corresponding to different brain areas. Maybe the successor representation one corresponds at least in the hippocampus, and maybe you have a purely model-free value learning in stratum, in basal ganglia, the stratum, for example, and there is a weight between this these two parts of the brain areas that you put at different stages of your brain system to eventually give you a final outcome of what decision you should make. Okay.
Really hard.
Yeah, I mean, what they will say is that so there will be some behavior observation that initially maybe animal is doing more towards the model-based, and because the animal is not confident enough about the behavioral rules, not confident enough about its knowledge in the environment, so it's trying to remember everything, trying to look at everything. But when you keep training and training the animal, and if you overtrain the animal, at some point the animal starts to forget everything irrelevant to your shot and just do a stereotypic conditioning response reflex. Right? So there's in this paper they want to feed some behavior. This model, of course, is a computational theory, but the behavioral observation is experimental. And this is actually very old 1990 paper. People showed that if you train a rat in this cross maze, and you test whether the animal is just always take one action or actually going to a particular space based on its understanding of this environment, you can just train the animal always start from one part of the arm and turning right to get reward, and then test it when you flip the animal to the other side of the maze. So if the animal really learn the model of this whole environment, when you flip the animal to the other side, you should still go to this location, right? But if the animal just remember what action to take, actually always turn right, right? And it will go to one location, it will go to the opposite location. And there is a switch of the animal's behavior if you test it in the early phase of the learning versus in the late phase of the learning. So in the early phase, the animal is doing more model-based, and in the late phase, if you overtrain the animal is just always take one action from
Learning model every time.
of course.
So very early time, maybe more.
Yeah, that actually show different thing. I'll say same in this paper.
You overtrain them with habits, but then learning the
I think it depends on some subtle nuance between different behavioral pathways, and it could be three stages. It could be initially just do whatever take it to get a reward, and in some intermediate stage start to learn the model of the task, and then just form a habit. I mean, it could be three stages. Maybe this is just too simple for a rat to do, right? To locate its reward in the That's why initially you see that animal learn the model. Yeah, and we'll stop skip this couple of slides because Albert already gave us a very good introduction about a continuous attraction network. There's of course one important thing is if we think hippocampus does encode state transition probability, like what's the implementation of it, right? How to the neural circuit encode the state transition probability. By state transition probability, you basically should encode a relationship between not only two states, right? You should not only encode state 1, state 2. You should encode whether two states are neighboring to each other or far apart from each other. So that's what transition means, right? So continuous attraction network is actually a very suitable neural network that do that, because in continuous attractors, whether two attractor states are near with each other or far apart with each other will have very different, very distinctive dynamics when the network runs, right? So basically, our idea is the hippocampus. How do the hippocampus learn the transition probability? You may actually form a continuous attractor manifold which sort of mimics the task structure. So through learning, you use some form of kinetic plasticity to connect all its neurons in a certain way to form a continuous attractor, and that connectivity actually reflects the state transition probability in this task. This is maybe one way that the hippocampus encode successive imitation or whatever variables related to the state transition, right? And I remember yesterday, I don't remember the details, but yesterday in someone's talk, I remember one student asked a question like, so if we have so many different neurons, right? Why does those neurons encode some information, operate in some very low dimensions, right? Or we can say this, frame this question in the opposite way. If we just need a low dimensional encoding representation, why do we need so many different neurons, right? Why do we just have one neuron, right? I think that's a very good question, and at least one answer of that, I think, is, for example, if you just want to encode one variable, one-dimensional variable, in theory, you can just have one neuron, right? You can have one neuron with a gradually change firing rate to encode one variable. For example, head direction in this environment, or place on a 1D linear polygon, right? But the problem is, if you really do that, of course there's some robust need to normalize problem, right? But one thing I want to mention here is, if you do that, you can't form a continuous attractor dynamics to tell you which one is near to the other state. So you don't have this dynamics to stay in a current in a certain state and encode the relationship between different states, right? So I think maybe and for continuous attractors by definition working in a very low intrinsic dimensionality, right? So that's a feature of continuous attractors. So maybe that's why, at least one reason that why you need so many different neurons operating in a low dimension. Okay, so this summary of part one is, I think this is the most important part of my talk today is first hippocampus, within hippocampus encode the spatial cognitive map that reflects state transition probability, and the hippocampal cells, the brain cells, performing successive representation, which is actually an algorithm in the middle between a pure model-based and model-free learning. And just a quick mention of the plasticity mechanisms that may be responsible for constructing such a cognitive map that reflect relationship between different states. So one thing I already mentioned is that because for any transition, by its nature, all transitions are directional in time, right? Because when you say you transition from one state in another state, you only go in one direction in time. So that's one thing that you really want to have with your plasticity. If your plasticity is not directional, it will be harder to constructing this sort of map in some scenarios. For example, in this scenario, when your behavior is very asymmetric, right? And if you just have a Haiping plasticity, you can imagine that you cannot use Haiping plasticity, a correlation-based plasticity, to get a place field like that, because Haiping plasticity is not directional in time; it's symmetric. Yeah, so you just have a Haiping plasticity. It doesn't matter which neuron, your post-acting neuron, your pre-acting neuron, which one fires first. As long as they're both fires, within a certain time window, you strengthen the synaptic weight. So you will always have a symmetric place field, right? So you need some asymmetric plasticity. And fortunately, we have one, right? So this Dr. Haiping already mentioned this, right? So actually, beside time-dependent plasticity, this is first reported by Harvard Macron and Bert Sussman in 1997, and of course later, Hu Lab as Guo Qiang, at that time working with Moving Pool, did a very systematic analysis quantification of this time-dependent plasticity. This is a very good, very interesting asymmetric synaptic plasticity, because if before the pre-synaptic firing, before the post-synaptic firing, you have a strong LTP, potentiation of the synaptic weight. But if it's reversed, if it's a post-synaptic firing before the pre-synaptic firing, you get the opposite effect, you get LTD. And in theory, you can think that this very asymmetric kernel of synaptic plasticity can give you something like this, right? Can give you something like this backward shifted place field, because what you can imagine that so this is reporting from say one cell in hippocampus. So if one say one cell, because by whatever reason, sporadically fire one spikes. And because there are a bunch of C3 cells, pre-synaptic C3 cells, before this post-synaptic C1 cell firing, and that leads to LTP, right? That is pre before post, and those synapses will be strengthened. But on the other side, because it's post before pre, although those cells also fire, those C3 cells, pre-synaptic C3 cells also fires, but they don't get LTP, even LTD, right? So you will have an asymmetric place field like this. But there is a big problem, a very big problem on this. The problem is that the time scale doesn't match, don't match at all actually. Because here, let's see, this is in centimeters, in spatial scale, of course, in centimeters. So this is in tens of centimeters. So typically, a rat runs, actually I don't know rat, this is a rat experiment. If it's a mouse, typically it runs like 30, 40 centimeters per second. Rat, of course, runs faster than this, but like 60, 70 or so centimeters per second. So this corresponding to a few seconds to maybe half second, so 100 milliseconds to 1,000 millisecond time scale. This is the behavioral time scale. But if you look at the STDP's persistent time scale, it's about 10 milliseconds. So the kernel's time scale for the LTP side is actually a little bit shorter. It's like 5 to 10, the time constant, 5 to 10 milliseconds. The LTD side may be longer, but still in the 10 millisecond order of magnitude.
If you train multiple times, you'll quite a shift.
If you train multiple times, no, this can't be solved by training with multiple repetitions. No, because it's always going to, if it's 10 milliseconds, like think about it, go, like this says for itself, fire like maybe 1 second before. Oh, you mean if you train many different times, like randomly shifted earlier. Yeah, that's yeah. I think people propose that, but the problem for this is typically you don't need to train that many times.
You need or
yeah, maybe not one-shot learning, maybe exaggeration, but few-shot learning. Typically, you see few-shot learning forming this type of place field, right? Sometimes even one shot, but sometimes few shots. But you definitely don't see 1,000 shots learning for this. Okay. So there's a time scale problem.
The behavior time scale.
Yeah, that's what I'm going to talk about. Yeah. So there are actually two solutions to this problem, actually. So one solution is to maybe there is some mechanism, some neural mechanism in the real brain to actually compress this activity sequence, typically in the second or 100 millisecond time scale into 10 milliseconds still. So this mechanism actually exists in the real brain. This is called theta phase precession. So because in hippocampus, there is, if you record local field potential, there's actually very nice theta oscillation in the hippocampus. So this is typically 4 to 10 hertz, and when the animal is running, when there is locomotion of the animal, is typically the high end of theta, so 8 to 10 hertz oscillation. And for each place cell, their activity is actually phase locked to a specific phase in this theta, within each theta cycle. And why we call theta phase precession is because the phase is actually not the spiking phase. It's not a fixed number. It's actually keep changing from when the animal first entered that place field, continue to run into the peak of the cell's place field, and then exit the place field. You can see initially, if you look at this blue spike here, let's align like this blue spike to the LFP signal. So initially, spikes tends to fire at the top peak, and then we start to move earlier and earlier and earlier. You see, next cycle is a bit earlier than the trough. When the animal is around the peak of the cell's place field, around then the spiking activity is around the peak of the oscillation. Then keep moving earlier. So there's nearly a 2 times 360 degree shifting, the whole cycle shifting of the theta phase spikes when the animal entering, getting the peak and exiting the cell's place field. And for each cell, this phenomenon exists. That gets you a very interesting thing is that if you focusing one theta cycle, right, and you start to see what we call the theta sequence or theta sweep. Like it's within one theta cycle, you'll see this purple cell fires first, this blue cell fires the second, and then the green one, and then the yellow one, right? So within this theta cycle, actually this sequence mimic the place field sequence of these 4 cells. And this is due to the theta phase precession of each individual cell. And this actually compresses the time scale of all these place cells firing sequence by 1 order of magnitude within one theta cycle. This theta frequency is about 10, right? So, and this falls within the STDP time window. And so people propose that with this theta phase precession mechanism and combined with like time-independent plasticity, you may get successful representation in hippocampus if you apply this plasticity with theta precession. Recently people have found some really, I think, really magical ways that still really understand how it works. It's like if you automatically train all the upstream MEC neurons with a gamma frequency, what people find is you can disrupt the theta phase precession in the hippocampus without changing the firing rate of each individual cell. So basically, you disrupt this fine scale sequence without changing the overall firing rate of the place cell. And and this manipulation actually disrupt the spatial learning of the animal. So sort of indicate that the theta precession might be important. Might be important. And the last thing is the solution 2 is you don't really compress neural activity sequence, but you actually have a very long kernel of synaptic plasticity. I was in the background. This is my colleague in Jennifer Madi's lab discovered that Katie Biner first reported this in 2015, and then in a later paper 2017, they called it behavioral timescale synaptic plasticity, BTSP. So what Katie found is if she recorded intracellular this individual whole cell reporting with patch clamp, then sometimes you see a silent CA1 cell suddenly becomes an active place cells. And this conversion, this transformation is triggered by a plateau potential, dendritic plateau potential spontaneously happen in some trial. So what is that event is? It's actually a dendritic Kelsen spike. So if the cell, this is a pyramidal cell of CA1, if the cell receives very strong input from this distal dendrite, you will open a lot of AMD receptors, also a lot of R-type voltage-gated Kelsen channel. And those channels work together to give you a gigantic influx of Kelsen and trigger that prolonged depolarization. And this is a plateau potential. Plateau potential can achieve few-shot learning, sometimes one-shot learning, to dramatically potentiate all the concurrent synaptic inputs within a time window to completely convert silent cell into a full-blown place cell. And the curve, as you can see here, the time scale, one interesting thing is the time scale for this BTSP, that's why it's called behavioral time scale, is the time scale of the BTSP kernel is in the order of second, not 10 milliseconds as in STDP. And also it's asymmetric. It has a very long, it has about 2 second decay time constant before the plateau, but only a half second, about half second to 1 second time constant after the plateau. So it gives you a behavioral time scale, also asymmetric plasticity. And also, this is, you don't only get LTP from BTSP, because that would be weird. Later they show that if you further test longer windows, you can also get sort of a matching effect plasticity kernel with LTD on 2 sides, but LTP in the middle when the plateau potential and present firing is close enough. Okay, so that's pretty much all I want to cover. So the summary is there are two solutions to give you asymmetric plate field in the heater chamber that may recall some state transitions in the past. So one is you compress everything into one theta cycle based on the phase precession and you apply 10 millisecond time scale plasticity, or you have a basically Kelson side trigger BTFP that give you a predictive map behavior time scale. Okay, thanks.